Okay. Um, Hello guys. So if somebody's watching, currently this is a test stream because OBS is behaving weirdly, my internet is behaving weirdly, so is my PC. I'm not sure why. Um, Currently it seems to be working. It is pretty stable. If I try to write stuff, maybe it'll go down. So maybe if I try to write, I don't know, the insert function, right? If I say like root of the red black tree, and then we link together the red black tree, and then a new node. Seems like it's fine, right? It's capturing everything. The kbps is stable. I think it's fixed. So I'm trying to edit a bunch of stuff to see if like that generates lag. Maybe if I scroll a lot and then I go to this other file and then it's only VS Code that I'm using, so no other program should be interfering with this. And OBS is now fine. See how there was no lag in that? And I think you guys can hear me very well. Let me see. You guys can hear me very well. Let me see. Yeah, you can hear me. So I think it was just a matter of um I don't know. I moved a bunch of settings and it seems to be working now. Um so let's throw in a Hail Mary and let's let's modify the title of the stream and go back to coding, I suppose. Hopefully nothing bad happens. So let me edit the stream information. Instead, it should be coding a memory allocator allocator from scratch. And then it's gonna have programming life. And then this is the final stretch, part two. Um, we may have fixed OBS. Okay, done. There you go. Okay, updated. I think that's, yeah, I think it didn't go bad in the time that happened. I can still hear myself. And the delay is not that much. Perfect. Okay. Awesome. All right. Well, I'm gonna leave the stream as is. I could stop and start again to tell everyone that, like, we started to stream again. I'm not sure if that's ideal because I don't want to like ruin the settings if they're currently working. Okay. So to whoever is watching, the one viewer we have, hello. Could be Cerny, Silnik, Vorsa, I'm not sure who. But yeah, thank you for sticking around. I'm so sorry for what happened before. Um, Believe me, I really like streaming and I like to interact with you guys and like code together. And I mean, I'm the one most affected by things like these. So it is not in my interest to have a bad stream or to ruin things. It's just that these things happen. So yeah. Before we start though, um I am asking for permission to grab a little snack to eat while we go back. And so give me 2 minutes. Give me 2 minutes. I think you can still hear me because I have my the headphones on or whatever. I'm currently filling my water bottle and trying to fill the water bottle. Great. So once this is filled, we can go back. Okay, I'm gonna also grab a spoon because it's potential. I potentially want to eat some. There we go. Okay. Hello again. Um. Okay. So everything is fine. Everything is fine. Everything is fine. Okay. Let's put this here. Ah. Hello. Rough morning. Rough morning. I was very hopeful today, and I was very happy today. But that little incident, you know, was a little bit difficult to sort out. Because of that, I don't think we're gonna have the time to finish everything in the memory allocator, but at least most of it. Okay. Um, yeah, I have frosted flakes. They're not sponsoring me, of course. I just like them. I just like frosted flakes a lot, and you know, I don't have milk, so I just eat them with a spoon. So I'll be eating frosted flakes from time to time, at least to refill in myself a little bit of the joy that's gone. mm, wait, actually, I may consider not doing that because I don't want to have people hear me chew. So I don't want to put you through that. SharifSegfaults. Let me see. If I munch on some. If I munch on some. Oh, it sounds normal. Okay. I'm so sorry. All right. Well, that was all. Perfect. So let's proceed. Let's proceed. Once again, I'm very sorry for what happened, but we are new people now. We have crushed the adversity, just like in crushing the frosted flakes. Okay. Um. Yeah. Unfortunate this morning. So let's continue now. Let's basically, since we haven't done anything today, basically, because we were trying to fix the stream, I'm gonna do a recap of the things we've done, which is mainly the fact that from our last session we had destruct. We only had these functions for parent and color, and what we did today's morning was add these guys to our code base, because accessing the struct for right, left, and size, but not being able to access it for parent is kind of confusing. It's like you have to say, oh, okay, right, I can access to the struct. Parent, I cannot. And for right, I need to first convert this to a block pointer and then access right. For parent, I actually don't. For parent, I simply call the function. For color, the same. But for left, remember to convert it into a block pointer. So the code base becomes super messy. It's simpler if we just have functions to access the data members. And then that also gives us the sort of side advantage that now we can change the order of the struct, change the way that they are organized or laid out, and then no behavior in our program is going to get affected. So Nick Vorsa suggested like, oh, maybe we put the color and size. That could be possible. I'm saying that I think there is no difference, but we could do that. and then simply update this function and this functions, and then we should be fine, right? Like everything would stay the same and nothing would really change in our program. So that's exactly what we want. That is the great life. And it's exactly what we have decided to do. We also transferred the code from the .h to the .c because while I didn't realize that we were actually writing it in the .h in the header file instead of the C file. And that's all. So we're having a problem here that says that there's an unknown type bool. And this is because I didn't remember that C++ doesn't have bools. So instead, we are going to create this enum direction, and we're going to accept a direction. So I have a small question on whether or not we can do something like this. Type def enum and then make direction be at the bottom so that I don't have to write enum all the time. And I think that's valid. So now I can just write direction. Yeah, okay, perfect. Awesome. So here inside of link, we're instead going to include the direction enum, and that's going to be left. So here, if left, or I guess that now we can just call this direction, which is an advantage, right? If direction is equal to direction left, then we, ooh, what happened? Direction, yes. And then 2 dots left. Ooh, do enums work differently in C compared to C++? Ooh, what a great question. So let's move to this workspace. Let's open Firefox. How to access numero of an enum and C. Okay, it's the same by oh. I see. Okay, let's read the Stack Overflow. You don't need to just do this. In C, there are no static struct members nor namespace. Oh, yeah, I forgot. Okay, C doesn't have classes, doesn't have namespaces. Okay, so you have to use the enum value directly. I see. Okay. So I guess one of the weird things about C or C++, depending on your view, so you can simply just say left. I see. Conflicting types for links. Previous declaration is here. This is the exact same declaration, question mark. Why? Is it the name of the parameter or something? That shouldn't be it. Okay, I think this is just the extension trolling me. No, it's not. Okay. So what's the problem? Oh, there's already a C function called link. Oh no. No. Maybe we can make it static so that it applies only to this file or something like that. No? UniSTD. So if I eliminate, yeah, so we have to link our, sorry, to change the name of our function because there seems to already exist a link function in C. Let's just call it T-link, like tree link. I feel that that'll just do the job. Let's just call it T-link, tree link. Yeah. Okay. Let me refresh the extension because I'm pretty sure that's trolling. Yeah. Okay, perfect. Yay. We did it. Okay, now. Okay, what do I need to do now? Oh, we need to translate all of this. Okay, perfect. I'm glad the kbps are back to normal. All right. I'm ready now. All right, we're gonna link in our tree the ghost node, which is RB tree, and the new node. The new node is the node that they passed us, so that's gonna be the block. And the direction we want this in is right. Now, to the root of our tree, we want to change its color. So block set color. We want to change its color to be black. So color to that's black. And of course, we don't have that so black, right? Perfect. And then we return the result. Now, we need to remember something, and that's going to be a to-do over here in the memory initialization. And it's the fact that since now we are passing to the arbitrary functions the ghost node, we need to allocate space for that guy inside of our heap, which means that init, it's going to have to allocate some space. So here, allocate space for ghost node in heap. We could also, instead of that, or simply consider storing it in the stack, right? And so that way we don't waste much memory. Or rather, it's not that we don't waste memory. It's the fact that we don't have to perform a memory allocation at the beginning. So if the user never uses the heap, then they're gonna be fine because, right, they don't really need it. So if we just put it in the stack, it's gonna be there. If we instead put it in the heap, it means that potentially we may have to perform a system call to bring sort of the initial bytes of memory. We will consider that. Just this is a to-do, right? So to-do. Perfect. If we leave that aside, then we can just continue, right? Then return from here. And after that, here we're told that we're going to navigate down the tree until we find the insertion spot, which is fine. And so while true, we're just gonna compare these two things. So we're gonna compare the value of the thing to insert and the current data. So this changes a little bit here in our implementation because what we're actually accessing is the size, right? So if the size of val, which is the new value, in this case block, is smaller than the size of whatever the current block is, then we want to say, okay, if the current one doesn't have a left child, that is, if the left of my current one is just a null heap pointer, Then we're going to link, so t-link, we're going to link together the current node with the new node, which is block. And now instead of the right, we're going to put it to the left, right? So left. And in fact, now that I think about it, this could be left or right. I'm just going to put it as left, right? True is not a thing in C. I'm so sorry, I completely forgot. 1. Okay. And then after that's done, we're going to be able to break out of the loop because we know that we've reached a leaf, right? At least in the terms of the left side. And then what we can do is we can make current equal to current's left child. So in the case we still have left children, we can simply go to the left. Perfect. Otherwise, what we're going to do is we're going to say, well, if the new value is greater or equal to you, I'm going to try and insert it to your right. If you don't have a right child, so if the current one doesn't have a right child, it's a null pointer, then we're going to make this element we're trying to insert its new right child. So link the current one to be the parent, and then the left guy, sorry, the new guy, which should be block, to be the child, and we want to link it to the right of current, and then we break. See how the code reads nicely? It's like, I like that. I like the fact that it seems rather intuitive. And now we're just going to make current. If this guy current did have a right child, we're just going to go down that right child. Right? Perfect. Now, once we're done, we're going to go and say, well, if the color of the current node is black, then we can simply return. Because we know that whatever if the current one is black, we cannot have any sort of problem, right? Because of this, well, let me think, is that true? Yes, because of the red-black tree rules. We thought about this before, but I just want to make sure. The root and leaves are always black. Yes, if a node is red, the children are black. All paths from a node to its nil descendants contain the same number of black nodes. Yeah. So if it's black, then we know that there's no problem, right? Whatever our parent is, black doesn't it means we're fine. Otherwise, we're going to have to solve all of the problems we just introduced with this insertion. And so now we're going to say while the new node, so block, is different from the start, from the RB tree, then we're going to have all of this code, right? K0. The K0 is the new node is the root, right? That means that we need to make the root black, and then we can return. So if the root of our red-black tree is equal to whatever the new node is, then we're going to say, well, ooh, okay, this is a little rough. Actually, no, it isn't. Okay. Then we're going to say, well, block, right? We need to update your color. So block set color, and we're going to set it to black. And we know that after this, we're done. There's nothing else to check because we reached the root. So we break out of here. Now, if, let's see what it says here. If there's no problem, we just continue. Okay. We just continue. Happy face. So if the color of our new node, which should be block, is different from red, right? Or you have that the color, BK color of the current one is equal to, I imagine, red also is different from red. Yeah. Pick a color current different from red. Then it means that we also have no problem, because the only conflict we could have is two reds coexisting. So now we make block equal to the current. So we go up the tree. Now we make current equal to its parent. So block parent for the current. Okay? And after that we continue. Perfect. Now we go case one. And for case one, I actually think I should rename block to be a new node, because it's a way more descriptive name and it definitely helps a lot. So let's set up the convention we had before. So case one is new nodes, uncle is red. And so what we're going to do is we're going to say, well, if the color of our uncle, and we have stumbled upon a function we have not implemented yet. So now we're going to implement that guy. And that is the uncle function, which belongs to the family members section. So here we have a section about family members, and it goes under tree modifications. So I'll put it under tree data access actually, and it's going to be called family members. We are a happy family. Okay. Grandpa is going to be one of the members, so let's implement all the family members now. You're gonna pass me the pointer of the block whose grandpa you want to know, and I'm going to return to you the grandpa, which would be the block parent of the block parent of block. Great, that's all. For the case of the uncle, it is a little bit more involved, because you need to know whether or not you're a left or right child, or like your parent is a left or right child. So what we do is, well, is your parent a left child, right? And what we do is we're going to say, well, if the grandpa of my block, right? Oh, sorry, this is in the header file. Why are we doing this in the header file? Okay, I'm just gonna create all the declarations, and then so the sibling is going to return a pointer to the sibling node, and it will accept a pointer to whatever block we're talking about and whose sibling we want to know. And then over here under tree data access, we're going to create the family members function. Perfect. And then we're going to do what we were doing before. So we're going to return the heap pointer to whoever the grandpa is. And now I'm going to turn the heap pointer to the block. And I'm just going to copy the code that we had before, which is return the parent of the parent. Let's now implement uncle. So for uncle, we need to accept the block we're talking about. And to discover his uncle, we first need to know whether or not the parent is a left child. And this would be a direction. Sort of parent. Hi Negvorsa, welcome. Yes. So I modify the title of the stream to be a test stream. I turned off stream, I played with the settings a lot, and now it's fine. Now it seems like it's working. It seems like the network is stable, my Wi-Fi is stable. Now it's not going all over the place, which is what's making me really sad, and like, so now it looks okay, which is fortunately the case. I'm happy everyone is back. It seems like more people are joining the 3 viewers, so we're coming back. We're coming back to the memory allocator, which now we're writing. So yeah, yeah. So this is the uncle, right? Then the way we're going to translate this is, since C doesn't have bools for some unknown reason, we're just gonna use the direction enum. And so what we want to know is our parent the left child? So is the left of our grandpa the same as our parent, right? If so, if so, then I want to know, uh, oh yeah, no. So here we just, yeah, if so, then the direction is left. Oh, sorry, I forget that we don't have namespaces in C. And if not, the direction is right. And so now what we need to do is we simply say, well, if your parent is indeed a left child, then you're going to return the right child of your grandpa, and that's going to be your uncle. So grandpa, and then left, sorry, right of that, right. And otherwise, you're going to return the left. So left, and then the grandpa of our block. Perfect. We have it, great. Finally, we need to implement the sibling. And for the sibling, a very similar thing we need to do. We simply need to know whether or not we are a right child or a left child. If we're a left child, we return our parents' right child, and vice versa, right? So we're going to return. It seems like we have a helper function called isLeftChild. So I think we can actually just use that instead of this. So isLeftChild, our parent, right? The parent of our block. If so, then do this. If not, then do that. Okay. I just want to take care of the columns. 89 columns. Okay. I try to keep the value below 100. Perfect. So we have the sibling now. And for the sibling, we're going to ask the same question. If I am a left child, then give to me my parents' left child. So the left child of my parent. Otherwise, give to me the right child. No, it's the other way, right? If I am left, then give me the right child. And if I am the right child, then give me the left child. Yeah, there you go. So parent and the block. Awesome. All right. Now the last thing we need to create is the left child function, and that's going to be under the node information section because it provides some extra information about the node that we don't necessarily have like completely available. I'm going to copy the doxygen because pretty helpful. And what we're going to return is a direction. So we don't have bools, unfortunately. So I think we cannot have isLeftChild. We actually can only have like what would the name be? It would be like node direction, right? Like a function that tells us whether I'm a right child or a left child. So I'm not sure what a good name could be. Does anyone have a suggestion? Let me think about it. It's like, for now, I'm just gonna call it Deer for direction. It's a really bad name, but fix this, like, name. Oh, wait. Do we have, is there a header that supports bools? So you're saying include std bool? Oh, dude, that's awesome. Let's go. Thank you, Neckvorsa, saving the day once again. Okay, so then I assume I can do bool? Ah, perfect. Okay, now we can do the left child. is left child, and now we can just pass to it the heap pointer of the block we're talking about. We simply need to assert that our block's parent is not null. So null heap pointer. Great. And now we're going to simply return, well, our parent's left child. Yeah, so we need to return, is the left child of your parent yourself? In that case, you are the left child. So here we also would need to include, assert.h, I think is the name. So this standard will, like, imagine it's from the standard library, so we simply include it here too. Great. I'm actually going to sort the imports this way. Okay, so we should have everything. Conflicting type sort is LC. Brother, what are we talking about? Implicit declaration is already here, 97. Oh, okay. Yeah, of course. We have not even defined it here. So for the node information guy, we're gonna have h pointer t, and then we're gonna have islc. Actually, no, it doesn't return that. It returns a bool. And now I imagine I need to move the header from here to here, which makes more sense. Perfect. And now what we're going to do is we're going to have the heap pointer t to be our block. And then we're going to assert whether or not our, like, the block's parent is... Oh, wait, no, that would be implementation, and we already have that. So I think we're fine. Now if we go back here, all of the problems should be gone. Unknown type name bool. Buddy, what are you talking about? Oh, there you go. The extension is just really slow. Sorry about that. Okay, now we know, now we have the isLeftChild function, which means we are in a great position. So now, if we go back to where we were, so here, case one, here. So if the new node's uncle is red, so if the color of the uncle of my block, which is not called block, is new node, although it's not really a node, it's a block, but it's okay. I'll change the name later. Let me actually include a to-do for that. Like, then we need to change new node name just for the sake of, like, simplicity in the translation between the two. So if the uncle is red, then what we want to do is we want to recolor the grandpa. Sorry about that. Recolor the grandpa. New node, and then we're gonna say block set color to be red. So we recolor the grandpa red. Then we also need to recolor the uncle. So we can set color. And I think the uncle we modify to black. Let's see. Yes, okay. Uncle and then new node. And then classes to be black. Finally, we need to make our parent, so bk set color of the bk parent to be black. Right. Perfect. Awesome. And finally, we move off the tree. And that implies, well, the new node will be now the current node, and the current node will be equal to its parent. Perfect. Parent of current. Yeah. That's it. Now, case 2 for insertions is the uncle is black. I think I'm just going to copy the comment. The uncle is black. And, ooh, my earbuds are dying. Yeah, they're low on battery. So let me charge them. It's the only microphone I have access to. So Hopefully they don't die. I'm gonna use one at a time. Perfect. So case two. Case two is the uncle is black and the new node forms a triangle with its grandpa. In that case, we need to determine whether or not this is a triangle and in what direction is it going. So what we're going to do is we're going to check if there's a triangle, press in that position, new node. And this calls for the implementation of the check if triangle function. So we're going to implement that one. Check if triangle is under the shape section. So let's do that. And we're simply going to return a char that checks whether or not, what sort of is the result of whether or not this is a triangle, actually, is what I want. Triangle. And you're gonna pass to me the node that we're talking about, so a heap pointer to whichever block you're talking about. And what we do is we're gonna say, well, if this thing doesn't have a parent, so if the parent of the block is equal to a null heap pointer, or we have that the grandpa doesn't exist, then this cannot be a triangle because the triangle involves a grandpa, right? Then we're going to return. And what do we return? We're going to return 0. 0 is going to be there's no triangle. -1 is the triangle is a left triangle, and 1 is going to be the triangle is a right triangle. So sort of related to their roles in the number line. So if there is no left child for this block, and on top of that, if this is a right child, and on top of that, the grandpa of my block to its left, let's see, what does it say? Node parent. So this is the same as saying, if I am a right child and my parent is a right child, is a left child, so bk parent, and then block, right? Then this is going to be, let's see, I am a right child, and then, so this is going to be -1, right? There's a left triangle. Yes. And so now we go to the other case. If I am a left child and my parent is the right child, then this is a right triangle. Return 1. Perfect. Awesome. All right, I think that's all. Finally, if it's none of these, then we return 0 to indicate that it's not a triangle. While we're at it, I think we can just implement all of the remaining shapes. So to check if something's a line, we simply have to pass the heap pointer to the block. Then say, well, if my parent doesn't exist, so bk parent of my block is simply a null heap pointer, or the grandpa of my block is a null heap pointer, then we know that we're in trouble, so this is not a line. Otherwise, we're just going to say, well, if you have that you are the left child, and on top of that your parent is also a left child, then it means that you guys are in a line. Block. So then we return -1 because it's a left line. And if instead you are a right child and your parent is also a right child, then we're going to return 1. Okay, what is the... Oh, it's not its left. It's LC. It's LC. And then here it's is LC. Perfect. And then finally we return 0. This arbitrary to vector is for testing purposes, so I'm going to delay it until we are concerned about testing whether or not we translate it well. But I think this is just a translation. The risk we have of translating badly is almost null, I want to say. It is good if we were to test it though. So let me transport these things to the C file because I, for some reason, always forget. that we are not in this C file. Paste. Oh no. I think I got rid of this thing without copying its content. Okay, Control C, and then I erase this, semicolon, and then here paste it. Perfect. Same thing for this guy. And then we erase all of the stuff that's here. Close, close, close. And then we copy, we paste. Perfect. Yay. Okay. I think that means we're done with, now this to do doesn't apply anymore because that was for the time we didn't have a bool. Let's go back to the place where we use this. So here we have insert, blah, 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 case 2, right? So for case 2, if our uncle is black and then forms a triangle, then we're going to say, well, if you actually form a triangle, then come into this case, right? If what you have is a left triangle, then I need to left rotate, and I forget that we have not implemented the rotation functions, so now we need to implement those. We need to rotate to the left the parent of our new node, right? Perfect. Otherwise, we need to right rotate the parent of our new node. Awesome. So what we're going to do is this, all of these things are helpers, but this is more like tree modifications. So I think we can just include it under here. So link, and then we're gonna have a rotate left. Let me see, where do we have implemented that in the original file we wrote a few days ago. There's a link swap. There you go. So left rotate. I'm gonna copy the doxygen so that we don't have to rewrite that all over again. I think actually, given that we now have the enum for directions, we can implement a rotate function and maybe make it universal. I'm not sure. Although that seems, that's a pain. Okay, never mind. Let's just do rotate left. Okay, rotate left. What it's going to accept is going to be, tell me which one is the node that you want to, or the block that you want to rotate to the left. First of all, we need to make sure that that block's left child, so bk left, that block's left child is not null, so that it actually has a child that we can, because the rotation is going to go through and we don't want that null pointer to be the root now all of a sudden. So now we want to set the parent of whoever our left child is, block, to be a null heap pointer. There you go. So basically, we're telling our left child, you, my friend, are going to be parentless. Like, we're just abandoning him. Let's see, if we do have a parent, if the parent of my block is different from a null heap pointer, then that means that we can link these two guys together. So we can link my parent. Let me see the battery of my AirPods. 9%. Okay, that's fine. We can link my parent with my left child. So I'm transferring my left child to, let's see, to my parent. I need to transfer the left child. No, that would be right rotate. We're rotating to the right. Why are we doing that? Oh, because I was looking at the code for right rotate. Yeah, okay. Yeah, this should be this should be right. This should be also right. Right. Then my parent is not null. I need the right guy. So here, bk right, now it makes sense. I need my right to become the child. Yes. Okay. Awesome. And I want to link them, ouch, in the direction indicated by, which direction? So I think we're just gonna get rid of, given that we now have bools, we don't need the direction enum anymore, right? Because, yeah, we can just use true for left, false for right. Because that's gonna simplify like our interactions with the isChild function. So left rotate, oh yeah, we don't forget about these. If left, and then this would pass to be a bool, it should be left. Awesome. And now here we go back. Okay. And then whether or not we link it as a right child or a left child is going to depend on whether or not we are left children. Okay. So once that happens, and I think this comment is extra, once that happens, we need to remember who our right left child grandchild, so right left grandchild is. So right left grandchild, and that's going to be the left of the right of my block. Right? So we first go to the right, and then we go to the left. So this guy that's at the bottom, we're going to link a bunch of stuff together. So I want to make my right child be my parent now, and I'm going to be the left child. Now I tell myself that I no longer have a right child because I'm going to transfer it to like I don't have him anymore. He's my parent now. So now I'll just do bk, not parent, bk right, I think, block right, and then we need to set it to be just a null heap pointer. And so we pass the null heap pointer. Perfect. And now we t-link again, where we're gonna pass, well, the block is now gonna be the parent of whoever the grandchild was. The thing is, in the process of moving our right child and like doing all of this crazy stuff, we get rid of the, like, we no longer have access to our grandchild. That's why we need to store the grandchild in a variable and then actually connect them together. If we first connect the grandchild, since it's going to be our new right child, we lose track of who our right child was. So yes or yes, we need a variable. And after all of that's done, we need to return to the user who the new root is, and the new root is my parent. Perfect. So rotate left, and then it should return who the new root is. Awesome. Now we proceed with right. So for right, we copy the dot again, and it's actually right. Right rotates the pointer, yeah. Then right rotates the tree. Awesome. And now we basically do more of the same. So pointer t, then we right rotate. Right rotate. Then we're gonna have a heap pointer to the block that we need. And I think now that we know how left works, we can simply copy this code and modify the accesses. So all I need to assert is that my left is different from a no heap pointer. Awesome. Now we need to access the parent of my left. So that would be the parent of my left. We need to make it, so now we set it, set my parent to be a no heap pointer. Now we can eliminate this. Here, if my parent, so bk parent, if the parent to my block is different from a no heap pointer, so it actually exists, Then we want to link t-link. So remember that link is already defined in some abstract library, I don't know where. We need to make the parent of ourselves the new parent of our left child. So bk left for our block. And then we need to discover whether or not we're a left child to know which direction we want to link them in. Now we store the left-right grandchild. So we store a heap pointer to whatever that block is. And now we need to access the right child of my left block. So that would be my left right child. So it would be my grandchild. Finally, we link together my left child with myself. So now my left child is my parent in the right direction. Finally, we make bk set left. So we forget that that guy was our child because it's now our parent. So instead of a null pointer, it should be a null heap pointer. Sorry. Okay, there we go. And then finally, we t-link this, our block with whoever our grandchild was, and we link them on the left. Finally, we return our parent, which is the one that is now occupying our position. Perfect. So that's right rotate. We need to also define them over here. So tree modifications. And I think the doxygen should go to the header file. Not sure if that's the convention. If I remember correctly, it is. So let's just put it here. And then over here with right rotate, I'm gonna do that too. I'm not sure why we put this here. So left rotate instead. Should be left rotate, not rotate. Left rotate. Okay. Oh, new message. Wait, how would you test all those functions? Have you ever used test-driven development? So usually, yes, it is very dangerous to implement sort of something and then relying on it. We have already written down all of this. Like this, we're just simply translating the code to the new code base. We wrote this in the first few days of the series of writing the memory allocator. And yes, we did create some tests to make sure that everything was right. So we have like all of these tests related to like, measuring whether the rotations were right. Left rotation, and this is the test for the left rotation. Right rotation, and this is the test for the right rotation. So we know that the original code does what it's intended to do. We are going to translate the tests too and then run them here. I'm simply doing it for ease of, like, because we've already, so some people, like, some of the other viewers have already seen all the process we went through to create the red-black trees. And since this is basically the exact same code, I don't want to bore everyone by trying to find a way to translate these cases. We're going to do that once we're done, just to for peace of mind. But yes, we have already taken care of making sure that our functions are correct. I'm simply just copying the code from one place to another, and we are going to use tests after this. It's just that since the interface is a little bit different, like here you can just create a red-black tree out of the blue. In the C++ to the right. On the left, since the red-black tree is embedded into our memory model and the whole heap and etc., it would be a little bit, not difficult, but tedious a little bit to translate all these tests. So we'll just do that. And then eventually, once we have time, we'll just translate the tests too. So yeah. Here we have tree modifications, the t-link, the left rotate, and the right rotate. For right rotate, I don't need the doxygen. Let me see. Yeah, it's already there, so we're fine. Great. Is there anything else we need to implement from the helpers? So the helpers link is already there, swap. So let's simply now that I think about it, like we should just implement all of the helpers and it would be like way easier. So let me implement swap over here. So swap simply swaps two nodes. The reason why swap exists because here in C++, we could just do like, you know, like my node is equal to your node, right? To your node. And then here in like some temporary variable, we save my node. And then over here, I say your node is equal to my node. The reason, so this is a very particular situation we have, and it's the fact that we cannot do this. And the reason why I'm saying we cannot do this, maybe we can, so correct me if I'm wrong, is the fact that in the C++ version, these are objects that we can simply sort of move around, right? This is a struct, so they all occupy the same space, and I can just modify their member variables. But it's not like I can move blocks around in our memory, right? I'm gonna have like a block that's very huge, and it's not like I can move it. It's not like I can just, right, modify the size variable and suddenly it's bigger. So we need to be careful with that, which is the reason why swap exists, so that we can like swap each member variable sort of one by one instead of just transferring the whole thing, which we cannot do. So yeah, let's see. H pointer T, H pointer B. And there's also a lot of intricacies that we have to obey. So here we have, well, we need to exchange their parents. So we need to update whoever their parent is. It's not like we can just do a variable swap and so on. It's also a little bit more intricate. So if A is a left child, then we're gonna set the parent of A. So set the left child of A's parent to simply be B, right? If A is, ooh, what do you mean? Expression must be a modifiable L value. Oh, yeah, there's no equals. This is supposed to be with a comma. Perfect. Else, so that means that we are not the left child, we are instead the right child. So then we're gonna tell our parent, we are leaving you, your new right child is B, right? We do the same for B, where we say, well, if B is a left child, then we're going to set the left child of our parent, to be A. Otherwise, if B is a right child, so else, we're going to set the right child of our parent to now be A. Great. Finally, well, I'm not sure we have swap in C++, do we? In C, sorry. Do we have swap? Oh, of course. Okay, we need to simply swap these variables. So we're gonna say bk set parent, the parent of who? Well, the parent of A. We need to set it to be B's parent. So bk parent B. Not having access to the swap is so annoying. Anyways, so temp, this is just to exchange their parents, bk parent of A. So now we set A's parent to be B's parent, and then we set B's parent to be the temporary variable. So TMP. Perfect. Well, there's sort of the problem that we're creating an extra variable when we don't need to. Can we change this? And the answer is I think we could just use the XOR trick, to be honest. Like, we set the parent to be the VK parent of I just don't want to create an extra variable. Let's, what did I do? There you go. Okay. So we set it to be a XOR of these two guys. Then this guy can go. Finally, I set B's parent to be A's parent. A's parent. And then I need to XOR that with my BK parent. And then I set the parent of A to be the same thing, right? To be this. Whoa. What did I do? Okay, select this expression and then go down here. Yeah. So what's going on is the parent of A is equal to, so this guy is the parent of A XORed with the parent of B. Then over here we have, who is the parent of A? Well, the parent of A is now this whole expression above it. So it would be parent of A XORed with the parent of B. And then we XOR that with the parent of B. So now by associativity, you have parent of A is now XORed with parent of B, which is XORed with the parent of B. And that is the same as, since a thing XORed with itself is 0, that is just the original parent of A. So here we're setting the parent of B to be the parent that A had previously. And so now that that's done, well, this is going to be, what is the current parent of A? The current parent of A is this expression. And then what is the current parent of B? Well, the current parent of B is A's old parent, which is parent of A. And so this is the same as by commutativity and associativity, the parent of A XORed with itself, and the original parent of B, which is equal to the parent of B. So then we managed to swap the variables without creating temporary variables, so we save memory. But I feel it's kind of silly. Doing this is pretty silly, so let's temp more clear and faster. Yeah. I think this is kind of silly. Not sure if faster, but definitely clearer. So let's just do that. Let's just keep it here. BK set parent. Okay, sure. Let's go with that. Now we need to exchange the children. So children exchange. We're gonna change the left child. Oh, I see what you mean. Yeah, by the function calls. A left. Okay, so we access the left child of A. Then we want to set its parent, so BK set parent for the left child of A. And we're gonna set it to be B. Finally, if, well, we would have to say if this is equal to different from a null pointer, no H pointer, yeah, there you go. If B has a left child, so if B has a left child, then we're going to set the parent to be the parent of the left child of B to be A. Perfect. And now we go to the right child, and then, oh, it seems like we need to swap again. So let me just use temp again. Temp being equal to the left child of A. And so now we can set the left child of A to be the left child of B, and then we can set the left child of B to be the left child of A. Perfect. Oh wait, to be temp. Yeah, temp. Great. Okay, we exchange them. Finally, we proceed to the right child. For the right child, the same story is told. I think we can simply grab these guys and then replace everything with right. Let's just verify that's the case. So these are the same. They form the same shape. So yeah, perfect. Right child. And we're done. Okay, so that's swap. Now we need to add it here to the header, where we simply add the doxygen. Oh, we don't have doxygen. Okay. I mean, we can just swaps two nodes. Which I feel it's pretty self-explanatory, but just to make it pretty. And then it's going to be a void swap, and it accepts the two things that you want to exchange. So A and B. Perfect. Right, so that should be, ooh, this is now a bool, and it's called left. Great. Okay, over here we have an error while processing. What is it? Unknown type direction in line 25. Oh, I just changed it. Okay, the extension is just low. Yeah, okay, perfect. So here, we have swap, we have T-link, we have grandpa, uncle, and sibling. Grandpa, uncle, and sibling. Sorry, give me a second. Guys, can you hear me here? Hello? Yes, I think you can. Oh, wait, we have, let's see, faster, no many function calls. Oh, we have new messages. Temp equals this, limited scope. Oh, yeah, sure. We could limit the scope of temp, but I just wanted to reuse it to do the other. Where is it? Here. Just wanted to reuse it for the other guys. We could do that if it's like better or something like that. Let me know. Let's see. We have another message. Fan Bjerg. Do you work as a programmer? Oh, I don't work yet. I am in college still. I'm a college student. And I mean, we're doing this just for fun. There are like thousands of implementations of Malloc out there, so we're not really contributing anything faster. But yeah, it's just for the sake of learning, and because like I wanted to learn more about memory allocation. So now we're all here, sort of like learning how to create a memory allocator from scratch. Let's see. You look too Chad. You look too Chad to be a programmer. Thank you. I mean, uh, thank you very much. But I feel like it's the opposite way, right? Like, being a programmer, I feel it gives you some, like a different view on things. Becomes more logical. So I like that. I like that programming is good. But thank you very much. Yeah, thank you for hanging out in the stream, and yeah, you can like ask any questions or say if you have an opinion, maybe the code looks ugly or something like that. Don't feel afraid to say it. We are all learning here, including myself. Like by that I mean that like Nick Borsa has been giving me a lot of tips too, and some idiomatic things about C, since I'm not very familiar with C, given that I program mostly on C++. So some things are different. So yeah, don't hesitate to ask anything like what we're doing, etc. Let's see. Like I study CS at my first year, and there's a high density of Java people, including me, bro. No, no. Okay. Wait. That's honestly that's interesting. Okay, so you're a first year. That's pretty good, dude. I mean, you have plenty of time. Plenty of time. I'm a rising senior, so I just finished my junior year, which is my third year of college. Just finished it, and yeah, I feel like what it takes is just the attitude, right? It's just your attitude to want to learn stuff, to want to do things. Um, I mean, the fact that you clicked on like a stream that's called coding a memory allocator from scratch, it's like, a good indication that like you're intrigued by programming. And I feel that's the main thing that you need, right? To have that curiosity that's gonna push you forward. So you can hang out, you can hang around and like learn with the rest. You can also leave if you want. Maybe you have other stuff, or maybe it's not as interesting to see someone coding than it is to actually to like code the thing yourself. Um, I assume at this point, Neg Vorsa must be like watching the stream and be like, no, 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 don't write it that way. What are you doing? But it is the nature of like, watching a stream of some guy programming. Um, but yeah, we can talk about that too. Let's see. I'm a bit scared of AI by the time I graduate. On one side, I'd want to do coding only as a hobby and do something else professionally, but I don't know what else I want to do. That is honestly one of the most valid comments I have ever seen. Um, if you have to talk about this topic, I feel a very similar thing. To be completely honest, I am a bit scared of AI. I am not scared in the sense like, oh my god, AI is going to take my job and like, we're all going to be homeless. Maybe a little bit of that, and maybe a little bit. I feel like the thing that I dislike about AI is that it's changing the programming world to something that is difficult to handle at the beginning. And by that, I mean, in order to sort of come to peace with AI, you have to be very conscious about your actions and you have to be very conscious like, I understand it can write the code, but I must review the code and I must understand what's going on at all times. Some programmers understand that, and it seems like it's easy to them to do that. For others, it's more difficult, but the people that do not really program, and this would reflect in like, your boss maybe at a company or like corporate in general, uh, have this very weird idea of AI that like, oh yeah, this guy is useless now. We should replace everything with AI. And that is the dangerous thought and the thing I am scared of when it comes to AI. Is somebody sort of using or thinking of AI as this thing that can just replace employees and all of a sudden everyone's gone. Not because you feared AI could do your job, but because someone else thought so. Um, so that's one. And the other one is even if that didn't happen, I feel there is a sort of joy to the mere act of coding, to the act of like writing the things on your keyboard and finding all of these dead ends. The profession of a software engineer is now changing a little bit where you don't really do much of the coding. You are supposed to do more of the planning. And I feel that is still a good thing. Um, the more attractive thing about software engineering ends up being the thinking. No, making sure that the system is working. How are these things going to interact with each other? Is the system going to support as many requests as we need? And for all of that, we still need people and we still need software engineers with a lot of experience. So I don't feel there's something to fear when it comes to having a job because you could only fear such a thing if you are if you're focused on simply writing the code and like you push your value to the mere act of moving your fingers. If you identify your value in your thought and the planning you do and making sure that you make the right decisions, interfaces, etc., I feel that's plenty of time, right? It is unfortunate though that it's changing. I honestly really like, as I said, the mere feeling of the keys, incredible. Um, but it is something that I guess we have to get used to. Part of why I'm doing this is because I'm currently in an internship, right? So I'm currently working at a company, and the feeling, it is my first internship, so it was a little bit of a crash with reality, in the sense of AI, where everyone was saying, use AI, right? Like, just let Claude Code do it. And where they said, like, at the end of your internship, we're going to evaluate you by the amount of tokens you use, which doesn't really make sense, right? Like, or like how much AI you use throughout your internship. It doesn't really make sense, right? The amount of usage of AI doesn't correlate with the quality of a product. And in fact, I would argue it is inversely correlated. The more AI you use, the lesser the quality is, because usually to use more AI, you just let Claude Code go. Like, you just let it go. You don't stop it for anything, etc. And I see people, software engineers at these companies, that have like 6 Claudes deployed at the same time. Things you cannot really follow, like, the code that they're writing. So you're sort of trusting, which, right, as time goes by, is really going to take a toll on the products and like companies produce. And in fact, we're seeing it right now. I don't think I'm able to name a product that has gotten better ever since a company adopted AI. So we'll see. I like to use AI as a learning tool and write it myself. I have tried using agents, but it's just not for me. Same, dude. Absolutely the same. um, as I said, they told me, like, dude, spawn another agent, spawn another agent. We have the coding agent, we have the planner agent, we have the agent that creates the React components, and it simply is something you cannot keep track of, and you cannot be responsible with if you just have like thousands of them running. They say, like, oh yeah, check the code, but how can you check the code if it's 10,000 lines, right? And then the next day your boss comes to you and it's like, all right, we gotta roll the next feature. So I completely agree with that. I find when AI writes it for me, it is easy for me to miss details during review. That is completely true. Writing it yourself is in the end, right, the thing that puts you the most alert. I don't know, it's complicated because it depends on the task. I just don't like using agents for every single task. Yeah, agree. Of course, if you're going to have like some really boring thing where you just need to, pass one thing to this other thing, sure. But those are also like boring tasks, even if you didn't have AI. So, so yeah. But yeah, using them for every single thing, this sort of new culture that's forming, seems rather harmful. And yeah, I mean, part of it is also adapting, but another part of it is finding a way out. And an example is like, right, this stream, like, at least for me, making these projects just for the sake of learning, saying like, all right, we're gonna code today, and we're just gonna like turn on the stream so that people can just join, and we can all code together, and we can look at the code, and I don't know, right? So I feel these types of things are good. Side projects are, if anything, the best way to find sort of the passion that you had since the beginning that put you into CS in the first place. But yeah, a little side talk. That's good. So good, 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 good. I don't know if maybe you have other opinions, but dude, yeah, I'm sorry that this is like the way you're feeling, because I understand sort of exactly how dooming it seems, but it is sort of a change in perspective where you simply focus your value on perhaps your decision making. And yeah, and help others identify that that's your value. So yeah, well, we'll see. Let me know. I also feel annoyed that this occurred right. Yeah, dude, I'm about to graduate college, right? So it occurred, and I'm like, all right, well, GG's. Like, what do we do now, right? But that's everything, right? It's just a matter of looking at things from a realistic but positive side. It is a little bit annoying though. It is a little bit annoying. But yeah, I don't know. It's interesting to see and think of. I don't know. the meantime, let me see. Let me check if there's anything else we need to implement. Um, yes, we do. Okay, we have. Um, so fun. I have a question. Like, are you familiar with like what we're doing, what a memory allocator is in that, or do you want some context on it, or do you just want to watch for a while and then leave? Like, let me know if there's something you don't understand, or like something you're like, oh, we should change this. Feel free to say it, or to ask, or whatever, and we'll spend time here. Um, let's see. I get accelerated learning at the small cost of my sanity, happiness, potential job prospects. People disrespecting my work daily. Yeah, I feel you. I feel it. It is. Um, yeah, I wouldn't know what to say other than like what we've already mentioned, and I feel it is a little bit sad too because companies, at least AI companies like OpenAI, Claude, etc., are making sure to sort of feed this narrative of like you're not gonna have a job, right? In 6 months you're gonna be gone, right? And although a little bit of thinking where you say, well, that's really not that plausible, right? We maybe don't have enough compute, or AI is eventually going to become more expensive, etc., etc., etc. Or thinking about the things we've been talking about. Instead, it's easy to simply take that at face value, right? Where you just listen to whatever the company is about to say, and you're like, all right, we're doomed. So it's also a fault of like the people that are feeding the narrative just for the mere fact that it benefits them a lot. Of course, the AI company is going to tell you that AI is going to be better than humans in the future, and and so on. Normies will still bring it up and tell you, okay, yeah, I mean, it is the unfortunate perspective, right? If you're not really an expert in a field, or you're not interactive with it, well, it is relatively reasonable to trust what the other people around you are saying. And if the news and the companies are always being like, yeah, no, you're gonna be jobless. Of course, everyone is gonna believe that narrative, which is, I feel, the danger of such things. But it is in you to have the mental strength to say, I know logically that this is not really the case, right? And that I can prevent this. That I need to simply steer my career towards something that's more focused towards a different type of value as my decision making, rather than the mere act of coding. And everything will be fine, right? Often, as children, right, parents will say, don't worry about the things you dress with, or like don't let anyone tell you that you're ugly, or things like these. And despite being such basic advice, it is nonetheless something that applies throughout your life. And in this case, if you're certain and if you can logically process sort of the fact that this is unlikely, that it's not like every software engineer is going to be out of a job, and that if you just change your perspective, things are going to be fine. Yeah, you just apply that same mentality. Don't let others tell you otherwise when they're also not part of the field, and maybe not as aware as you could be. I will believe in AGI anytime League of Legends fixes their. Never played League, but valid feeling, I suppose. We'll see. We'll see. Yeah, I mean, um, it is a good metric, though. It is a good metric. But yeah, let's see if we have. Oh, this Doxygen comment for some reason filtered over here. Um, chicken line, chicken triangle, and then we need to implement the min node and the max node. Yes. Okay. Okay, we need. So now we need to find the min node of a child. And the comment says find appropriate section for this, guys, but I think this is outdated because this is the the node information one. And I think these fit in the node information section. So we can simply, let's see, we can To find the mean node, we would need to return a heap pointer to whatever the mean node is. So what this does is we pass it a subtree, and this is going to find the minimal node in that subtree, which is another way to say that since this is a binary search tree, we just go to the left. Right? So if the block is equal to a null heap pointer, then we're just going to return a null heap pointer. Right? And then while removing, while there is a way to move to the left, so while we have left children, then we know we can travel to that left child. So we're just gonna travel to that left child. So block will now be equal to the guy that's to my left. And then finally, once we reach the end, we're gonna return whoever we know is the leftmost child. The block is of course a heap pointer. And now we simply need to add this. I'm gonna copy the oxygen over here. And oh, new message in chat. Wait, give me a second. Let me transfer this, and then I'll read the message. Hello? Where is this? Huh? Oh, here it is. Okay. Yeah, I was getting a little scared. There you go. Perfect. So wait, do we not have a? Oh yeah, we do. We have a doxygen for this guy. So let's apply the doxygen here. And then we have bool. Max node, grandpa, da 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 da. Great. Okay. Now we have to implement the max node. But first, let me see what the new message is. The client is the most buggy POC I have ever interacted with due to the graphical fidelity. It is akin to a polished. Damn, these are some strong feelings about the LOL client. Interesting. Hopefully I can solve it. Although, given the fact that whenever companies have tried to put AI into their products, the products become worse. I'm not so sure about it. But what we can do is wish them the best, right? Because everyone is benefited if they improve the client. So that's great. Block. There you go. So let me copy this oxygen to this other guy. What we're going to do is we're instead going to return a heap pointer to the max node. And we're accepting a heap pointer here. Good. Okay, perfect. So what we're trying to do now is we're having the heap pointer to the max node. And then block. Yeah, okay. So what this function is going to do is when we pass it a subtree, that is, we give it sort of the root of some sort of subtree, we are going to find who the max node in that subtree is, which, since this is a binary search tree, we just need to go all the way to the right. So null heap pointer, then we're going to return the null heap pointer. So if whatever they give us is an empty subtree, then we don't need to, we just tell them, yeah, there's nothing here, brother. Like, what are you talking about? Otherwise, if we have a right child, it means that we keep going because we haven't reached the end. And how do we keep going? Well, we make the block be our right child. And then finally, we return the block. Perfect. Okay, that's the max node. And I don't think there's anything left for us to implement except for this arbitrary2 vector. Awesome. I think we're done with the helpers. So let's go back once again to the place where we were doing. There you go. Case 2. So where is case 2? Case 2. So we are currently implementing the red-black tree cases for insertion, right? And then after that, we need to move up the tree. Move up the tree. And so what we're going to do is, oh my God. The thing that this swap was referring to the std swap, not the swap function that we have over here. So we just went in and implemented swap for nothing, but okay, I guess like we're going to eventually need it. So I'm glad we did it. But yeah. So for now, let's just do heap pointer t temp, and then this is going to be the current node. And then we make the current node be equal to the new node. And then finally make the new node equal to temp. Perfect. All right. And after that, we continue. Good. So instead of moving up the tree, well, no, we are moving up the tree. It's just that the rotation made it so that our child, which is new node, became our parent, and that we became the child. So now we simply go to the new node, right? And that's it. Perfect. Case 3. So case 3 is the uncle is black in the tree, and new node forms a line. So whenever, well, with its grandpa, I suppose, but we sort of implicitly understand that's the case. Okay, so now we do the same thing, but now instead of calling the triangle, we call the line. So line direction is equal to, well, we're going to check if this is aligned. And if it indeed forms a line at this new node, then the line there, if it forms a line, that is, this is different from 0, then we're going to recolor the grandpa of my new node. We're going to set the color, so bk set color, and we're going to make it be red. So now the grandpa is red. And we also need to set the color of another guy. Oh, chat message. Give me a second. Parent. BK parent of the new node. Perfect. And we want to set it to black. Okay, my node's color is going to be black. Finally, if this is a left line, this is the less than 0, then we want to right rotate our grandpa. Otherwise, we want to left rotate the grandpa. The grandpa of who? Well, of us. And then at this point in time, we know that we're done with anything that could happen, so we just break out of the loop. Finally, here we return result, but we don't really need to. Previously, we had coded insert so that it returns to a pointer to the node that it just inserted. But remember that the user is the one providing us a pointer to whatever they want to put in, which means they already know what it is. So there's no need to return. And with that, our insert function is done. Yay, we have a red black tree. At least the insertion of a red black tree inside our heap. All right, let's see. In this case, their client has been awful since way before AI was known for Vincines. Yeah, usual corporation. There was a greater value proposition in adding gacha features and new overpriced skins for the whales. Okay. My dream job would be fixing that client. But that your dream is probably dead given my very vocal frustration with its quality. Okay, I'll do it for me. I'll do it for minimum wage is crazy. Yeah. Dude, I wish I had the same passion towards, towards a lot of things as you do with the League of Legends client. I guess like being a frequent player, you identify like a bunch of things that may be wrong. But yeah, it's the disadvantage of like corporations, sort of focusing more on this greedy aspect of what it is to be a company. Surely profits are something important when it comes to being a company, but it reaches a certain point where you really have to ask yourself, Given that we're already big, given that this is already, we basically have a kingdom, right? Um, think about different aspects, right? Not only social aspects, etc., but the clients that have made you who you are. And I feel this applies to everything, right? Not only companies, it applies to people, right? It applies to every single life. So it is a good core concept to have in mind, in fact, now that we look at it. If you mention like League of Legends is forgetting about users, and like corporations are changing stuff, it is a good sort of north star to have for yourself. You know, independent of what happens, to stay conscious of the people that have helped you, to be grateful, and to focus more on the quality than the quantity. So yeah, coding is when coding is truly solved, then that client can be fixed at a cheap cost. Exactly, and that's how you know that's never gonna happen. So it is sort of like you know, the implication there is AI will never replace software engineers, because if that were to be the case, then the League of Legends client would be completely fixed, which seems to be an invariant of the universe. Uh, so no, never played League of Legends, as I say, but I feel the same could be said of Microsoft products. You know, the day coding is truly solved, we're gonna have a quality Microsoft product. I'm sorry for clowning on Microsoft. Like if somebody in the audience um, works at Microsoft, I'm sorry. It's just it is easy sometimes to dunk on Microsoft because of current decisions and stuff. But yeah, and the YouTube front end. Oh, the YouTube front end. That's a new one. Never heard someone criticize the YouTube front end. Uh, I like it. I feel like I like the YouTube front end. And it's like, you know, it just like displays the little squares. I can just scroll around. Unless you're talking about it being very slow. I have discovered many bugs with it as a YouTube power user. Okay, yeah. I assume that like yeah, I am in the situation where like maybe I don't have as much experience with YouTube. Um I watch YouTube from time to time, but yeah. So it seems like you have a YouTube is burnt into my screen. The YouTube logo. That's so funny, bro. Yeah. Pretty good, pretty good. I mean, see, but it's good that you have problems to solve. You know, there's like a goal in mind. If you ever become a software engineer, like once you graduate, um, you'll be able to know where to aim, right? I better work at YouTube, fix all the problems they have, or League of, or like Riot Games and etc. It's very fun. Um, I just now realized that we have 5 viewers. Damn, is the peak of today. Previously we had 7. 2 people left. Who knows? Hello, 5 viewers. We're doing. Oh wait, new follower, Lifeborn77 or Leafborn77. Um, Let me know if I pronounce it correctly. Thank you for following. So now we have how many followers? We have 12 followers, people. Let's go. um, on the road to the most subscribed Twitch channel. But yeah, no, this is great. To everyone that's joining in, we're creating a memory allocator from scratch. We are using red black trees as the underlying data structure to sort of manage the free blocks. So if the user requests a given amount of memory, we're going to surf through the red black tree until we find a free block of memory that is the best fit to their request. The thing is, we spent the first like 3 days of this series or 4 days of this series coding the entire red black tree class in C++ so that we would know how a red black tree worked. Because before this, I didn't know anything about red black trees. I knew they existed, but I would always use AVL trees. But red black trees are more memory efficient, so they're better to use in our memory allocator. Currently, we're just all the code we produced in those first 3 days, translating it to fit with the fact that this red black tree that we have in our memory allocator is going to be sort of embedded inside the memory allocator. Like the blocks in memory cannot really move, and like the blocks themselves are the nodes of the red black tree. So it's not like there's a node storing a value. No, the value is the node. So we have to accommodate for a couple of these things. The code is basically the same nonetheless. And yeah, that's all we're doing right now. Feel free to ask any questions you have, to say anything you have. We're also having like a normal chat. You see like how Fambier was, talking about League of Legends client. Feel free to do whatever. Tune in and out of the stream. I know it's a little bit, difficult to like watch somebody code and so on. At this point, it's been like what, 4 hours of stream. The first 2 hours being spent trying to fix OBS. So I'm glad we fixed OBS. But yeah, that's all. So with that being said, I'm going to copy these comments that I forgot to copy because they introduce a lot of very good context on what we're doing in this while loop, at least. So yeah. Perfect. Okay. Awesome. Let's go now and implement find. So find is the one that we're mainly going to use to see if there is indeed a sort of, if there is a block that we can use. So for find, it's hopefully going to be simple, question mark. So the current one is going to be the root of our red black tree. So the root, and this guy cannot be a root. This actually has to be, what did I do? This actually has to be a arbitrary type, and then we just pass it in like arbitrary, right? Perfect. So the root of a red-black tree, we need it. Too few arguments. Oh, okay. We also need to find who the lower bound has been up until a given point. So that's going to be a knowledge pointer. And then here we're going to say, well, while we still have something to explore, we're going to say, well, if, right, if the size they are requesting is smaller than the size of the current block we're exploring, so if size is smaller than the block size of current, then it means that we have found a new lower bound. So the lower bound is now going to be current, and then current will just move to the left. So we'll move to the left to see if we have something that fits better. And this is actually bouquet left of current. Perfect. Otherwise, we're going to say, well, if you have the case where size is actually bigger than the size of the current block, what you want to do is you want to move to the right, right? Not register as a lower bound because this is smaller, so we cannot really use like this block because it cannot satisfy the request. So we simply move to the right. So we move to the right of current, and then after that, on else, which we tell the compiler it's an unlikely case, just to favor the branch predictor and tell him like, buddy, it's unlikely this is going to happen. This nonetheless is, I think this is a C++ construct. Okay. Does anyone know if there is sort of an equivalent to sort of this macro thing to unlikely? It doesn't really do much. If I remember correctly, this is just something that you can use to help the compiler, but usually the majority of compilers actually ignore it because it's not like you can just change the branch predictor. Your CPU already has a branch predictor. You could organize the code differently maybe, but yeah, usually this is like something not that useful. I like to include it just for the sake of it. Let's see. Let's try to look it up on the internet. Stream unstable again because I opened Firefox, but we came back to normal. Great. Is there an equivalent of unlikely branch in C? So this is C++, this is C++. Ooh, likely and unlikely macros. I don't know if I feel comfortable with extracting my knowledge from a LinkedIn post, but we're going to try it out. In C and define two interesting macros, here's what they actually do. Yes, GCCs. I just need to know the name of the original thing. Built-in expect. Okay, to give hints to compiler about which branch of a conditions for when you write if likely. Yeah, brother of mine, what can we know what the name of okay. Like this is a specific case where we actually know this is okay. I guess we can use the AI overview, sure. Um Honestly, I think we can just skip it. It's not gonna make much of a difference. I just like to include it, but if it's gonna make our code look that ugly, I prefer to not do it. So, beauty over everything, I suppose. I don't know. Not in real life, but at least for the code. Actually, that's not the case. Don't put beauty over everything when it comes to your code. Usually, sometimes, by trying to make your code beautiful, you actually make it like less performant. But it's usually for me, it's a good indication for me, Sharif. Okay, Sharif for Sharif. Um, the beauty of your code correlates with sort of the decisions you've made and like how well things are going. So um, I do have to say the code seems very beautiful right now. Okay, let me copy the doxygen for find, and I think have we defined find yet? We actually have. Okay, perfect. Is it data to find the fit for, and I'm gonna add the brief also here, brief, which is returns the element whose key is a lower bound to the past key. Okay. Oh wait, did I say lower bound? Dude, it's an upper bound. What am I talking about? Dude, and this is also in the code that we have. Damn, I cannot believe I missed this. This shouldn't be LB, this should be UB. Okay. Next time, next time, yeah, no. Shoot me if I ever make a mistake like that again. Because the distinction is like very, very big between the two, and that would be a mathematically inaccurate statement. So, UB. Okay, perfect. Now we have yet to move to remove, and remove is going to be the last one because after that we will be done with a red black tree class, or well, not class, but like our embedded red black tree and the whole memory structure stuff. And after that, things are going to be sunshine and rainbows because the red black tree was like the most difficult thing to get to work. So yeah, give me 1 second, guys. Let me just go to the restroom real quick. I'll be back in like 1 minute. right, I'm back. Um, Hopefully everything is going well. Remember, if the stream is like laggy or something, let me know. But I see here that the kbps is stabilized. Not sure what was happening this morning. I'm just thankful it didn't happen again. Okay. Um, Let me eat some frosted flakes before we keep going. One more, one more, one more. Look, Nick Versa. Why not just is size more equal? Um, yeah, you're right. I feel like we could just do that. Um, it ends the execution early, though, but I think it's fine if we just do it like this. Um, yeah. I mean, I guess I have no problem with that. The reason, now I remember, the reason why we had done it like that here is because we accepted a comparator. Here we were accepting a comparator. And in the case of that comparator, um, I got lost again. Oh yeah, and for that comparator, right? Comparator in C++ like usually returns 1 if it is strictly smaller and then 0 otherwise. But we wanted the case to be smaller or equal to rather than greater or equal to. So since we couldn't really change the fact that the comparator behaved that way, we needed to create the extra case. I guess we can definitely do it this way. So sure. Although it finishes execution early, but it's going to be really unlikely, so probably won't happen. Yeah, agree. Let's just eliminate that. Thank you, Nick Vorsa, for the suggestion. Let's see. Let's try to now implement remove. This was the one that, together with insertion, it left a trauma in all of us, and all the people that were there, when we were coding the red black tree. So what we need to do to remove something in a red black tree is we first remove the element as if it was a binary search tree. And like, not as if it was, because it is a binary search tree, but just eliminate it as you would in a binary search tree. So we find the minimal node in the right subtree of our node, of our block. And then for the predecessor, we simply find the max node in the left subtree, right? And finally, we need to decide which one of the two is going to inherit our throne. So that's going to be the heir. And the heir is just going to be a successor. And if it's not the successor, then it's just going to be the predecessor, right? So if we don't have a successor, then just let it be the predecessor. So if we are deleting the only node that's left, we need to, let's see, if the heir is a null h pointer, and on top of that, it's not even, then the block is equal to the root of our red light tree, then we need to, okay, so here we had allocated some stuff. So here on the C++ side, we had like allocated nodes and everything, but we are the allocator. What we need to do is not really delete it, just mark this spot as in use. And there's no way to mark the spot as in use. We simply make the root of the red black tree be equal to, what's the name? Just be undefined, right? So this thing, ooh, what a great thing. So, oh yes, thank you, Nigvorsa. Thank you. Yeah. These are not pointers. They need to be the null age pointer. The amount of bugs, we would have had just by missing this line. That's why yesterday I was so scared of doing the bit shifting and instead implementing these functions. It's because of this. Thank you so much, because I usually stupid. Um, so there's something that we need to address, people, and it's the fact that we currently don't have a function to set the root of the tree like directly. Like if I want to set the root itself, I think we can just create like a little guy, little helper, that just sets the root, uh, given a red black tree. So the reason why we need this is because remember that the root is not like, it is a specific node, but we only have access to it as the left node of the ghost node. So it's better if we simply, because it could, maybe tomorrow, it could be actually the right node by some sort of decision we make. For example, the fact that right is before left in the memory block, which means that we wouldn't need to store the left information. We could just put, right, since right occurs first, we could just fool the program into thinking that we have a full node, but only include the size and the right value, and then that saves us memory or whatever. So I'm just gonna put it this way. So simply block set left for our red light tree, and we're gonna set it to whatever they give us. So h pointer t root, and then that is gonna be the new root. Perfect. Here we are. So now we want to set the root to a null heap pointer, and then finally we return call to undefined function. Oh, okay, sure. Where is root? Where is root? Where is root? Here it is. Void set root. Set root accepts an entire red black tree, and then it also accepts a heap pointer to whoever you want the new root to be. I guess that the names, well, shadowing helps us with that. It's fine. Actually, no, I don't want to take the risk. I feel I'm just gonna do new root, because there's already a function called root. Although shadowing could fix it, I just don't want to risk it. New root. Great. All right, let's go back here. We set the root and then we return. Now, if we do have an heir, then we're just gonna swap, but in the sense of a tree, right? We're gonna swap the node, which would be our block, and the heir, right? So we just swap them, just like we would do in a normal VST. And then we actually need to preserve their colors. So like the color is linked to the position. So same thing as before, color, color. I think that in our definition for color, we can do whatever we did before, where we declare this as a type def. This is an enum, and then color down here. So that way we don't have to refer to color as enum color, and we can simply use color. Yes, 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 and yes. Perfect. Done. So here in our implementation, yeah, there you go. Color and then sort of temporary would be equal to whatever this guy is. It should be the block's color. So bk color. Then I'm gonna grab the color of our block. And after that, we're going to set the color of the air. Oh, sorry, of my block. Set the color of the block to be the air's color. So bk color for the air. And then we set the air's color the airs color to be the temp that we saved from before, and it's gonna get killed here, right? The temp variable, so we're fine. Now after that, we need to get rid of something called the double black in a red black tree. Hopefully most of you are familiar. If not, let me know. But in order to get rid of the double black, we're gonna have to go through a huge adventure, and by that I mean around 100 lines of code. So yeah, the double black is like a little sneaky guy. He is definitely not somebody we want to have in a red black tree. So let's see. We're going to have this comment is a warning. So let's read the warning, the ominous warning in all red. Let's see. It says node is now thought of as the double black node. Oh, okay. So it was just like informational. Yeah. So node, or in this case block, right? This block that we stored in the block variable is now the double black node. So what we're going to do is while forever, or while true, now that we have the possibility, which by the way, I remember I wrote some while one. There you go. I just want to change this to true just because that's what I'm used to. And I don't know, it looks prettier, I guess. Here, while true. So we're going to do this forever until we are aware that the double black is gone. The case one is if the color of the node you're interacting with, which would be block, is red, then you want to link this node's parent. You want to basically make it a null pointer, right? Make its whatever that guy is a null pointer. So it's not loaded block. So null pointer. And then we're gonna make it is lc of block. Great. Finally, we delete the node and then we break. We don't need to do a delete because things are already in memory. Let's see. Setting colors after swap. Is this right? Yes. So this is where the code, like where the red black trees start becoming really weird. Because whenever we make a swap, say this one's red, like this guy is red, and this is its successor, and its successor happens to be, I don't know, black. We need to swap everything about them except for their colors. So the ideal scenario is to have 7 here. 7. Oh my god. Why is this so thick? Is to have 7 and then 4. So like we swap them and then we make the colors be what they were before. Right? So if we go back, we swap 7 and 4. So the red needs to stay here. So we swap them. And then we make them exchange colors. So now this guy is black. And then the other guy is now red. So that's why we're swapping them. Because you need the colors to stay the same. If the node that you eliminate preserves its color, then you could be violating, you definitely will be violating, in the case the colors are different, one of the red black tree rules. So it's the reason why we set the colors after they swap. That's all. Maybe 7 and then like 4 or something like that. Okay, cool, perfect. Okay, let me reinstantiate this tree just so we have it if anything. Save. Yep. All right, perfect. Case 1. Let me make this. There you go. Case 1, and then we break. For case 2, which is if the node that's currently infected, right, is the root of our tree, then we need to change the color of the root to be black. Okay, set color of block to be black. And remember, block is the same as root, so in the right it says root. Here I just put block. All right, case three. Case three is where it where it gets a little bit how could I describe it? Laughable? I don't know. So if the color, look at this case. Look at this case. If the color of your sibling is black and both of your siblings' children are black, then you need to change the color of your sibling to red. And if your parent is black, you transfer the double black to your parent. If not, just make it black. And then you need to remove the double black that you previously had. So this this is like why deletion and like removal from red black trees was the thing that was an extreme pain for all of us. Um because it's the most annoying thing in existence. Um but it's good that we learned about it. So let's see. If the color of your sibling is black and the color of your siblings' children, your siblings' children, hello, 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 there you go. Your siblings' children, so this would be the left child, right? And the left child of your sibling is black, and the right child of your sibling is also black. Hello? What's going on? Why are we canceling on this guy? Oh, yeah. We need to close the if. Oh. Where is this bracket finishing? Oh, here. It shouldn't. It shouldn't either. There you go. That's what we want. Perfect. Wait, what? Oh, there you go. This, and then we add a parenthesis here. Awesome. Okay, and then we actually code. Okay. So what we're going to do is we're going to set the color. We're going to set the color of our sibling. We're going to set it to red. The new double black. Okay, we need to determine who the new double black is. So I guess we create a heap pointer to who the new double black is. We make it null at the beginning because we don't know. And if the color of our parent, and then we pass in the node, which would be block. The color of our parent is black, then it means that we know already who the new double black will be, and that is my parent. So we transfer the disease to the parent. Otherwise, we simply make the parent black, which should be completely fine. So bk set color of who? Well, of my parent. So bk parent, and then block. We're gonna set it to black. 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 There you go. Perfect. Finally, we move the previous, the current double black. So remember that we transferred the double black to the parent in this scenario. Then we need to remove the double black that was present before. So if the double black happened to be a leaf node, so a nil, then we have to follow a bit of a different procedure, I think. Let me see. Let me see, why were we doing this? Oh, no, okay. In this case, the code simplifies, and it simply gets to, Control-Shift-K, simply gets to, well, if there is a new double black, then we simply make our current block be the new double black and repeat the entire process again. Otherwise, break out of the loop. We have gotten rid of all the double blacks. So, okay, what's going on here? We had this variable in the previous code called is double black nil. So, is double black nil will always be true if you wanted. So, suppose you delete a leaf node, not a nil node. That's technically the leaf, sure. But if you remove one of the, I actually think I can pull up the drawing. It's way better. Here, if you want to remove, say here, one of the leaf nodes, say this guy, it's gonna be fine, right? The problem is that the current, the code behaves differently if what you're removing or treating is a leaf or one of these upper nodes. If it's one of the upper nodes who is infected with double black, then you leave it alone. You just don't do anything to it. If instead it's a leaf node, then you need to delete it from the tree. You need to like get rid of him. So you like eliminate him. So that's why we had the is db nil, the nil being like one of these nil, implicitly nil leaves. And it's because if what you wanted to remove is something in the leaf, you first remove it, nil. But it needs to remain in the tree as sort of like a construct, which is why we were keeping track like, oh, is the guy we're treating with a nil, right? Is he eliminated? And then at the end, we needed to actually delete him from existence, right? To delete the node entirely. And so the thing is, with our new code, that's actually not something we need to do because we don't need to deallocate stuff from memory. We are the allocator and the allocate. We are the allocator and the deallocator. So we simply forget about that block, which is to say it is not reachable through our red-black tree, which is to say the user cannot touch it, right? We cannot provide it to the user, which means the block is occupied. So yeah, that's how we distinguish between free nodes and allocated nodes here. Blocks here in our memory allocator. If they are reachable through the red-black tree, it means they're free. If they're not, then it means they're occupied. So it is not inefficient because we don't need to know whether a block is free or allocated up until the point where we want to allocate or suffice a user's request. But at that point in time, we're just using the red-black tree, so it doesn't really matter. Okay, let's continue. So case 4 is if the color of your sibling is red, so here is a block instead, is red, then I hate this to swap now. Because that means we need to do like the whole, okay, color TMP, right, color TMP. Then we make it equal the color of the parent of myself. Then I'm going to set the color of my parent to be the color of my sibling. So bk color and then bk sibling. Well, sorry, the sibling, whole block. Great. Perfect. And then finally, we set the color of my sibling to be sibling of my block to be exactly what's stored in temp. Great. And so now, once we have swapped the color, we need to say, well, replace my parent's child with, or like rotate the tree in the opposite direction to me. So if, sorry, in the same direction as me. If I am the left child, then rotate it towards me. Left rotate. And then we're gonna rotate our parent. Otherwise, we'll move it to the right. So rotate the tree to the right, right rotate, and then it has the parent of the current block. Perfect. And then we return. Or well, we continue, sorry, because the double black could be somewhere else. Yes, perfect. All right. So, case 5. Case 5 is one that treats this very weird thing where it distinguishes between the far sibling and the near sibling. Same thing is what 6 does. So these are a bit like convoluted cases. So we need to get the far sibling. So, sorry, the far, what would that be? Like my nephew, right? Like the child of my brother is my nephew or my niece, right? So let's do far. Can we just call them nephew? Far nephew? What? Yeah, far nephew. This is going to be LC of the block. Right? If this block is a left child, then I want to access my siblings, right? My siblings what? So if I am the left child, then I want the right children of my sibling. So BK right of my sibling. Otherwise, I want the left child of my sibling. Right? That's it. Perfect. Was that the logic that we had? Sibling right. Oh, what? If I am a left child, yes, I want the right, and then otherwise I want the left. Yes, perfect. And then my near nephew, right? It's gonna be just the opposite. This is gonna be if I am a left child, then I want the left one. And I just want BK left of my sibling of block. Otherwise, all I want is the right child of my sibling. Right? Perfect. So now what we need to do is account for this case. So after we've obtained those, if the color of our sibling, if the color, here we go again with like the super convoluted cases, is black, and not only that, but the color of my far nephew is black, yet the color of my near nephew is red. Near nephew is red. What we want to do is we want to set the color to red. Sorry. What we want to do is like we want to do a convoluted thing, but yeah, if my near nephew is red, then we proceed, right? We perform a swap. What do we swap? Well, we swap the color between the parent and the sibling. So that just means set the color of who? Well, of my sibling. And to what? Well, we're gonna set it to red because they're swapping colors, right, with the near nephew. So right here, the code on the right is swap colors between the sibling and the near nephew, right? That made it easy because we had STD swap, but now we don't, so I don't want to do that. So let's just do set color, and then we set the near nephew's color to be black, right? So they just exchanged colors. because the conditions already tell us what their colors are. Perfect. Set colored, no color. Okay. To everyone that's joining the stream, hello and welcome. We are coding a memory allocator from scratch. We're using a red block tree as the data structure to store our free blocks. So that's why right now you see me coding a bunch of stuff related to a red black tree. And that's because that's going to be the most important thing that we're going to need. And yeah, so currently, if we are a left child, we want to rotate the tree to the right, right? And so where we rotate it at our sibling, uh, block. Otherwise, we need to rotate it to the left. So basically, we rotate it in the opposite direction of ourselves. So rotate the sibling to hi. Okay, there you go. Left rotate the sibling. And then after this, apply case 6. So case 5 is one of the only ones that doesn't get rid of the double black or do anything to sort of change things. It just modifies the tree so that case 6 can be applied. Let's see, Nick Vorsa. Line 174 and 175 again have the do you mean these two? So in this case, I think we do have this fine because this is the is it a left child function, so it just returns a boolean. So we should be okay. Let me know if that's not what you meant. But yeah, let's see. Let's recompute. So once case 5 applies, notice that we rotate the tree, right, in some sort of direction. What that means is that now our far nephew is no longer our far nephew, and our near nephew is maybe some other random guy. So now we need to recompute them. That's why we're gonna have these here. Perfect, but these are already declared, so we're just gonna do that. We recompute them, and once we recompute them, we're free to use case 6. So case 6 is not really going to, whoa, buddy, what's going on? Redefinition of, yeah, but we already removed the, okay, the the C extension is really slow. Thank you. Okay. Case 6. So now we need to swap, let's see, the color between my parent and my sibling. And for these, we do need to swap. So let's just do color temp and then make it be the color of my parent. So the color of who? Well, of my parent. And then what we're going to do is we're going to say, well, set the color of my parent to whatever my sibling has. So the color of my sibling. After that, set my sibling's color to whatever we stored in temp. And that should be it. Let's wait for the extension to catch up to our mental speed. Yay! Okay, perfect. Now, that we swapped them, well, we're going to rotate the tree in the direction of ourselves. So if we are a left child, then we're going to rotate the tree to the left. So we left rotate the tree, the subtree that starts at our parent. In the other case, we right rotate the subtree that starts at our parent. Perfect. So you just rotate in our direction. After that, we need to remove the double black from the tree. The thing is, we don't really need to do that. We simply need to sort of forget about that guy. And that is done by just, let me think. Okay, case 6 resolves things except for when we actually need to remove. So I think that I'm actually wrong. I think we do need these places where we do the is db nil, because currently, although we don't need to deallocate anything, we do need to tell our parent that we are no longer here. So that means that we would have to grab t-link. Yeah, we need to t-link our parent, so the block parent here, set it up with a null child. So we basically still, we're still his child. We're running away from home because we are the ones that don't want this parent anymore. And then we determine the direction based on whether or not we are the left child. And we are block instead of node. Perfect. And after that, I think there's nothing else we need to do. Yeah, is DB nil false, I guess. I guess, sure, that's, sure, I'll give it to you. And now we need to change the color of the far sibling child, so the far nephew. Far nephew. We need to set its color to be black. And perfect. I think, ooh, what is the capital S? What is the capital S? No camel case in my code. Okay. And then we break. So I think because we need this step, I'm just going to go to the places where we have is db nil and make sure that I included them. So this one is not a conditional here. So this is in case 3. Case 3. And indeed, we did not include that. So we need to tell the parent that we're no longer its children, its child. We're leaving home. And so we link the parent with a null pointer on the left or the right, depending on what our place was. And after that, we set didn't yield to false. Perfect. Next one. Next one occurs in case 6. Oh, okay. So those are the only 2 cases. We were lucky. Great. I think if we are to trust ourselves, which is a little bit too much to ask, we are done with remove. Seems like we're done. So everybody, I think we have done it. We have finished the red black tree embedment into our heap. So now we have the entire red black tree there, and we can use it through the interface for the red black tree. There's only one thing that I need to resolve, at least for myself, something that is not very clear to me, and it's the fact that, let's see. Okay, why is this guy complaining that he doesn't have an implementation? He has a little underline. He's in, there's no implementation of me, please help me. Why? Arbitrary fun, UN32. Oh, I think it's because we pass in an arbitrary type instead. And then, yeah, there you go, arbitrary. Perfect. And then here, the same thing, arbitrary t. And then there should be an arbitrary. Arbitrary corresponding to red-black tree. And great. Okay, I think we have everything we need. So actually, now that I realize, we have a whole Git repository, Git remote. Yeah, so we should have been adding all of these things to Git. I completely forgot. So let me just commit this as like a new, feat added red black tree. My bad, guys. I should have done this before, and then we need to push. Okay, I'm gonna push to origin. Yeah, okay, we we need to be more careful about that. I guess, yeah, I have to be more careful about that. I think we're fine. Okay. Let's just do Okay, okay. So this is a breaking point. This is a breaking point in our journey. Let's eat some frosted flakes to celebrate. So it is a breaking point because the Reblec tree is the fundamental data structure for our memory allocator, right? And now what we need to figure out is like little details and how to actually use the Reblec tree. I'm seeing, oh, damn, we have 8 viewers. Dude, 8 people. Hello, everyone. Um, Coding the memory allocator. We just finished coding a red-black tree because that's the underlying data structure that's going to keep track of which blocks of memory are free. And now we are going to move on to sort of finishing the memory allocator, I guess. I mentioned that there is something that it's not very clear to me, and that's the fact that we sort of created this arbitrary type because to these functions you cannot pass any node. We need to pass to it the ghost node. Um, and so because of that, um, like I want to make it a separate type, but it has the same layout as the heap pointers. I just don't want us to be like, oh, insert, and then what do I pass? I'm gonna pass the root of the tree. Because you don't pass the root of the tree, you pass the ghost node. So the ghost node is like the RB tree. The root is a node, but the RB tree is represented by the ghost node. I tried by making sort of this type definition RB tree, but I think that let's actually test it out. I think that if I go somewhere and then I say like RB tree and hello, um, what's going on? Oh yeah, we haven't included. Yeah, sorry. Include. If we include. Okay, so if we include the arbitrary header, right? Oh my god! Whoa! What happened? Damn! 27 errors introduced by just bringing in the arbitrary header. Oh, because the arbitrary already. Okay, yeah, sure. Already includes the header. So I guess we're just gonna have to. I forgot to include the pragma once, dude. I'm so stupid. Sorry about that. It won't happen again. Please don't kill me, man. Yeah, we're gonna have pragma once, and I think that solved it. Yes. Okay. Uh, yeah, it's fine. Okay. So, as I was saying before the import interrupted our beautiful moment, here you go. So, if we do arbitrary and then insert, and say I pass to it some random heap pointer type value, like I don't know. Say I create some variable heap pointer t, my guy, and my guy is just a null heap pointer. And then I try to pass my guy, and then I try to insert my guy. Right? So it doesn't matter, right? We're just evaluating the types. Notice that like it allows me to do this, and I'm not sure if I want to do that. Andrew Kraevsky. Oh, hello. Welcome to the chat. So your message just now. Can't you create a struct with one value as wrapper? So it is what I was thinking. The problem is, so the whole reason why we have a ghost node is because, and this is the explanation, like our program will need to provide sort of the initial node, right? If we make the program keep track of the root by pointing, ooh, why is that line so thick? If we make a program point to the root, we have a problem. So if we store a pointer to the root, the problem is that when a rotation happens or something like that, say a right rotation, then this guy moves sort of downwards. Then this guy is now a child of this guy, right? And then this thing, so this pointer still points to that same node that we just moved. This is going to be pointing like over here. And then this guy is going to move up. So if we rotate the tree, the pointer that the program is holding is still to this node, but this node is no longer the root. And the red-black tree doesn't know who is holding pointers to a given node, right? Because, I mean, it's not like you can just ask like, oh, who's referencing me? And so we have that problem. To update the pointer the program is pointing to, we simply employ a ghost node. So the ghost node is going to tell the root, you are not a full tree. You're actually a subtree. And what that does is if the program points to the ghost node and we perform a rotation, in our rotation code, we have, or sort of we are mandated to update the parent of, sorry, this is supposed to move here and this guy is supposed to move here. There you go. We are mandated to update the ghost node, telling him the subtree has changed. The root of that subtree is now a different one. And the red-black tree is aware of the ghost node because quite literally, right, the red-black tree is the ghost node. So now the root gets updated and we are all happy. The program just points to the ghost node always. So the ghost node needs to be a node because our interface implies that we will interact with our nodes with these functions. So they already expect a heap pointer, right? And they expect like a bunch of stuff. So if we replace it with a single, with a, like a struct, we're not going to be able to access that. And if we replace it for something else, then we need to create special cases inside the rotate function. So over here, we would need to create like a special case, something like if, so say this, right? We're linking the parent of my block to the right child of mine. So if we were to make the ghost node special, so a different thing other than a node, then we would need to include special cases. We will have to go to T-Link and say like, okay, if this is the ghost node, then all of this behavior changes. And everything that uses T-Link would need to also change. Right, so if you want to set the color of whoever your parent is or whatever, wherever we access a parent, it needs to change because the ghost node cannot, right? It's a ghost node for a reason. We're not supposed to modify it. So it goes into all of these cases, right? Strychnid, hello, welcome to the chat. And yes, the ghost node is stable and it's never moved. Yes, exactly. But when you perform these modifications, if you were to treat the ghost node as like a different type, you cannot use these functions on it, right? You cannot say like, oh, update the child of the ghost node. Because here, for example, you would need to update the child of the ghost node so that it points to the new root. But then you wouldn't be able to do that. So now the rotation code and the T-Link code need to account, okay, if the thing that we're, so it would become really bad because then we would say, well, if the 2B parent, right, is like not a ghost node, right, not a ghost node. And on top of that, it has a right child, and we need to include this guard everywhere. So it would be really bad. It's also the fact that we don't have like a universal, like, right? We could have multiple red-black trees. We will only have one, of course, because it's a memory allocator and we only need one. But just for the sake of the design, we want this red-black tree to be versatile enough that we can use it somewhere else. Um, and yeah, so I think the solution could just be from our memory strip, dedicate like, oh, shoot, wait. Dedicate the first few bytes to a reserved ghost node. Something like the ghost node is always going to be there, and he's just going to leave at the beginning of our heap. And we just don't allow anyone to, right, to be allocated there or anything. And that's easy to control, right? Because you just say like, all right, here's my ghost node. I just wanted to differentiate them, right? Because these functions should accept only the ghost node and nothing else. But rather, since we cannot have a special type for the ghost node, we cannot just like enforce that in the code. We need to remember, do not pass anything other than the ghost node to this guy. Which I guess it's fine. I guess it's fine. Because we can just name the ghost node RB tree so that it's natural to us. Like, oh, let's just insert inside the RB tree, right? My guy. Wrap the ghost node in another struct and unwrap it at the start of every function. Ooh, okay. Oh, is that what? Oh, wait. Is that what Andrew was saying? Sorry, Andrew. I think I didn't understand your idea. If StrictNet is now pointing this up, um, I'm so sorry. I'm so sorry. No, yeah, that would make a lot of sense. That would make a lot of sense. Thank you so much. I feel, yeah, that is a good solution, right? Is there anything that stops us from doing it? I don't think so. So I think we're fine. Yeah. Guys, you're the best. Thank you so much. So let's create just a struct over here that simply stores the heap pointer um, to like, you know, the ghost node or whatever, um, like node or like block, and then we just name it arbitrary type. Yeah, and now everything makes sense. Because now, oh my god, yay! Okay, this is great. Once again, the beauty of your code illustrates sort of like good decisions, which means that now we can make it so that like arbitrary can I just okay, now we need to change the name of arbitrary. So the arbitrary is exactly that struct. And so what do we name? I guess we can just name it ghost node, right? Like, yeah, ghost node is equal to whatever the arbitrary has inside. Hello? Why are we not auto-completing? Okay, that's fine. Block. So, because this type def conflicts with whatever we defined before. Yeah, there you go. Arbitrary.block. And then every single reference to arbitrary after that is to the ghost node. Right? So I think ghost node, and then ghost node. Oh, yeah. Root. And then here we have ghost node. I guess I'm just gonna do. Actually, let me just replace everything. Yeah, there you go. So it accepts an arbitrary, and then we simply accept arbitrary.block. So get the root of my arbitrary and set the root of my arbitrary. We simply need to access arbitrary.block. Yes, and so now, wait, were those the only cases where we use the arbitrary type? Let's see. Up here, where we changed it. Down here and find, okay. But we don't need to decompress it because we just need the root, okay. And remove, but remove only interacts with the root of the RB tree, and so we're fine. Okay, that seems great. All right. All problems in computer science can be solved by another. Yeah. Yes. Dude, the famous phrase. Yeah, exactly. Every single problem in that is actually the greatest example I have seen of that principle being applied. Um, other than like page tables in virtual memory and whatnot, but it's, yeah, this little trick, incredible. Little things you learn as you go in life, I suppose. I don't know. Um, so, so I think we can add like a little function here that just allows us to, since we're thinking about these things as objects, right? We just have a constructor or something like that, like create RB tree. And for that, we simply return like an arbitrary struct and include as block. Okay, this is gonna be painful to watch. Actually, let me think. Ooh, we have a problem. We have a problem. Do we have a problem? Let me eat some frosted flakes to think. I think we may have a problem. Mm, let me think. Oh, new message in chat. Let's see. It's not really interaction. It's basically distinct type, but without extra language features. Yeah, yeah. I mean, like it's a very, like it's not like the greatest example of something like that. It is funny to think about it that way. It's funny to think like it's some level of interaction that just suddenly solved everything. But I am here to deliver horrible news. Horrible news. I'm gonna eat more faucet though to deliver the news. There's a reason why these things are heap pointers. And the reason why they're heap pointers is because they expect the thing to be in the heap. So since every single memory block will live in the heap, this thing makes sense, right? Because, right, a heap pointer to the block, and all of the members assume that that is something that lives in the heap. So what they do is they try to convert this to a block pointer, which is basically like, right, go to the lowest address in the heap, add the offset that the heap pointer is telling you, and then actually like interact with the header of that block. The problem is that it's assuming, of course, it's a heap pointer, so it lives in the heap. So you grab the lowest memory address of the heap and then add to it the offset that the heap pointer is telling you to add. The thing is, like, with us, this thing just lives nowhere, right? So I think we're just gonna have to do. I guess it's not bad news, right? Because we can still get the benefits of the type. We simply need to make sure to insert or like, yeah, insert ghost zone at address like 0 or something like that. Maybe not address 0 or like practical address 0. And by practical address, this is something only we understand, so this comment will get deleted because it's bad to leave it in the code base. By that, what I mean is we don't know what the starting byte of the heap will be. It could be some random memory address, and the heap, or at least the blocks inside it, need to be 8 byte aligned as per the spec, which means that we need to introduce some padding at the beginning of the heap in case we ever, you know, like, in case we ever have a start address that's not actually 8 byte aligned. So practical address 0 is like the address 0 of the heap after the padding is applied. That's what I mean by this. So don't forget about that. This comment needs to go because practical address is not a good word. I understand. But for now, we just leave this here, right? So this is gonna be our to do. And yeah, I think we would be fine with that. So it is the best of both worlds. Well, not the best, but like it's the combination of both worlds. This is great. This is awesome. Okay, perfect. So let's do what we need to do. So we first, this function is going to be called when we initialize sort of the allocator. First thing we do, we reset the breakpoint. Right? We tell it to say like, all right, heap currently 0 size. Right? Oh wait. Oh, Strictney, thank you so much for following. Let's go. Now we have how many followers? 13 followers. Yay. Okay. That's awesome. 14 followers, actually. Never mind. Thank you so much. And yeah, you can tune in to future streams. So currently, first thing we do is we reset the pointer, or like, yeah, the heap pointer or the heap breakpoint to 0. Now we need to sort of increase the breakpoint to accommodate for ghost node, right? And so what we can do is how much will the ghost node need? So in our design, this is the way we are. Ooh, there's a bunch of arrows everywhere. We need it to have size, left, right, parent, color, and then the user data could be 0, and then the size. So I think we're gonna need, let's see, 4 plus 4 plus 4. So 4 times 4, 16. And then 16, we're gonna need 20 bytes. Okay. Sorry. There you go. Okay, so I think it's sbreak. Yes, sbreak. That we use to increment the size of the breaking point of the heap. Let's see. Just in case you don't know, your yellow comments font is really badly appears in stream. Oh, really? Oh no. Wait. What do you mean? Let me see. Because this morning we were having problems with OBS. It was doing random stuff, and it was being very laggy. So it's possible that something like that is occurring. Let me take a look in another computer I have here. Oh, yeah, that looks horrible. What? Why does it look that bad? Oh. Yeah, what is going on? I'm not sure. Okay, so I think because previously it wasn't doing that, like in the previous sessions we've had, at least I think. I am very scared to stop the stream to fix it because this morning we spent 2 hours trying to make the stream not laggy. So yeah, I'm scared to do it. And let's see, as a temporary fix, maybe you can change the colors to something else. Probably. But okay, now I would need to edit like the better comments extension. Which I mean, I guess it's possible, right? Like, I'll do it for you guys. Better comments. Better. Ooh, where is the settings file for this guy? I think it's here. Okay, high plain text tags, and then we can edit the tags in the settings of JSON, and then we can probably specify a different color. So this is the to do tag. There you go. Let me grab this guy, and then I'm gonna add it here to know that this is the one that we had before. Let's try this color, because it seems like I changed the colors in the past, which is interesting. Okay, if we apply this color, what will it look like? And then let me reload the window. Let's wait. Let's wait. Oh, that's way better. It's a little orange. I think that's better, right, guys? No. Wait, why? Okay. Yeah, it's really bad. So if I apply red, like hello everyone, will this be seen very badly? Yeah, like, well, hello everyone looks better. A little better, not the best, but why why is it targeting the like those specific ones? Let me just pick some random color. Some oh sure. To do. Let's just go. RBG color picker. Let's just pick some color that's like nice. Maybe we can make it like we need a maybe like this little yellow that's not so bright. This hex. Let's see. Will that work? Change it and then reload the window. Red on black. Yeah. No, I'm so sorry. Here on my screen, it looks very well. Oh, now it looks way better than to do. I think we can live with that. Yeah, I think we can live with that. So as I said, it's because of the stream settings. Like right now, what I see on my screen, it's like this red, beautiful. It looks shiny. it looks very well. But it is the stream settings. It's temporary for now. We have no red comments, so like right now, so we can just do to do, right? The to do is the important one. So we're not gonna have any red comments for now. So we can just leave it like this. Okay, seems like it's working. So I'm gonna close it here. Great. All right, let's continue. Let's continue. Okay, so we want to increase our heap pointer by the amount needed to accommodate the ghost node. We said that amount is 20 bytes. But actually, before we even think about this, we need to add padding. So we need to add padding to the heap. We simply need to do mem sbreak. We're gonna sbreak by how much? So currently we have this macro that we created a few days ago, the align macro, that simply aligns a given address to the next multiple of 8. So we can grab the address of the heap's load guy to the next multiple of 8, and then augment by that much. Oh wait, I think we're already doing that. We're doing that here. Yeah. Okay, I remember now. I remember now. So currently, we're not doing. We don't want to do anything in init. The reason is because it is very possible that the user, like, there could be a user that just has a program that doesn't use our allocator. That is, they have no need to use the heap and they always use the stack. And we would be allocating all the stuff we need for the allocator unnecessarily. And for that reason, we can simply just, instead of initializing everything in init, we can just do it inside Malloc in the first call to Malloc. There is a trade-off to consider here. So let me know what you guys think. So this is a question. And it's the fact that, okay, on one side, you have sort of no allocations in minute, which provides you with, like, better memory usage for non-heap programs. But on the other side, makes malloc bad because we need to check if this is the first time calling malloc. On the other side, we have use in a minute for allocations. Then we get bad memory usage. But malloc doesn't need to worry about checking if this is the first time. So it would be like a trade-off between either having those little bytes of memory, which are basically nothing, but affect potentially the branch predictor with malloc, which is also negligible, maybe, right? It depends. It adds like nanoseconds, if anything, or the other way around. Both seem pretty negligible. I am more inclined to go for the better memory usage. So just check in malloc if this is the first time, every single time that you call malloc. And if you're calling malloc enough times to the point that that is important, then you're doing something wrong. Like, I feel the search in our red black tree already like sort of eclipses that if by miles and by like a lot of time. So I think, yeah, I think I'm just asking a stupid question. We can just detect whether or not this is a first allocation and then do it here. If you guys disagree, let me know. If you agree, then I'll assume you guys agree. Once again, I'm just a college student, so there's a lot of things I could miss. Like, there has been a lot of things I've been missing. So, like, little mistakes here and there. So let me know. But yeah, let's see. Okay, we're introducing padding, which is doing exactly what we needed to do. It aligns it to the next 8-byte address aligned here. And then we allocate space for the user's block. Ooh, okay. This is a little bit of a different thing. Let's see. Message. But it's a good question. If you have an arena allocator, for example, the malloc path should be the fast one. Yeah. Okay. I agree completely. Yeah, I guess it's not that stupid of a question. But in our case, it becomes negligible. So yeah. Let's see. So we detect whether or not this is our first allocation. Align. I was showing it a few moments ago. So align, you pass it an address or like some number, and then it just rounds it up to the next multiple of 8. So if I do like a line of 3, then this is going to be equal to 8. And then if I do a line of 0, this is going to be 0. If I do a line of 16, it's going to be 16, and so on. So it just passes it to the next multiple of 8. That's what a line does. And so what we're doing here is we're saying to the current address of the heap, right? Align it. Find the next 8-byte address, and then just increase the heap pointer by the amount of bytes we need to in order to get to that address. So we're just introducing padding. Then we allocate the space for the user's block. This is like certain thing we had written previously. So I'm just gonna put it down, okay? We're introducing padding. And let's just have something here that sort of says, for now, assume this is the first allocation. So let's just worry about what would happen with the with that allocation. Wait, you said add extra parentheses to a line. So you mean this? Do we need that? Because currently the brackets of a line already enclose the memory heap low in the macro. Okay. Wait, is there a difference? Like, why do we need to? Oh, okay, I see. Because it's possible that we use a line somewhere else, and then this guy gets matched to whoever is on the right, and then it messes up everything. Okay. Is that the reason? Let me know if that's the reason. If I got it wrong, let me know. That may be the reason from my perspective. Thank you very much, Nick Vorsa. Yeah. Okay. Perfect. So now we're going to introduce. Yes, we have the padding. Assume for now this is the first allocation. So what we do is we introduce the padding, then we need to allocate the ghost node. And for that, we're going to need to increase the pointer by, so we're going to merge these two calls because, like, you know, system call twice is really bad. But for now, let's keep them separate. We want to expand this by 20 bytes, which is what the struct, like the length of the struct. But every block is going to be 8-byte aligned. So we just want to align whatever 20 is. And rather than 20, just to make it a little bit more versatile, the size of block header plus the size of block footer. We just separate that space. Oh no. One of my keys broke. Okay, that's fine. Let's see. Anyways, the way you articulate your thought is crazy good. Don't lose it. Oh, thank you so much. I one of the reasons why I started like streaming, because it started last Saturday, is precisely to improve that a little, to sort of narrate my thoughts better. Also to have something to look forward to after I go to like my internship or whatever. I don't really like to code there. So these projects are very nice and learning. So yeah, but thank you so much. Yeah, let's see. Continue with this. So we have the ghost node. And okay, for the ghost node, we allocate the space for the header. Then we allocate the space for the footer. No space for the user space because this is going to be a ghost node. And then we actually need to populate that space. And so what we can do is, does this thing return something? Yes, it extends the heap by increment bytes and returns the start address of the new area. Okay, perfect. So I need this start address just to know where the ghost node is going to live. So this is going to be a heap. Okay, a heap pointer type that is just going to be sort of like ghost node. I feel like, well, let's not call it that. Ghost node block. Right? This is the block that we're going to use to store the ghost node. But remember, this is a heap pointer. So it is an offset rather than an actual C pointer. We simply need to subtract from this value the beginning of the heap. So name heap load. Perfect. And so now that we have this, let me check that the parentheses are not wrong. Now that we have this, yes, we are going to be able to, it's probably better if you call, yes, I agree. That's why I said like these calls, we're gonna merge them together because like performing two system calls unnecessarily is really bad. For now, I just want to keep them separate. And actually, I think you're right. We should include a to do that tells us like, you know, merge the two, as break calls. But for now, I'm gonna keep them separate just for ease of thought. Right? It's just like easier to think like what about what we're doing right now. And then once we have the logic, then I'm gonna just compress them all together. Um, so yeah, we have the ghost node block. We know where it starts, and now we simply need to say, well, for the block header, interpret ghost node. Actually, we have the macro of the block pointer. So since this is a heap pointer, right? We cannot really access it as a pointer. So this macro just makes it like, okay, right, convert it to an actual C pointer so that we can deal with it. Why would we want that? We would want that because we want to modify the contents of the header like directly. And the reason why type name, oh, sorry. It's this way. There you go. So what we're going to do is we're going to tell it, interpret this pointer as a block header, and then we're going to start modifying its like the little guys, right? So we need to set, I guess, okay, because this guy, the ghost node block, is still a heap pointer. So we can just use like the, block set color and then like set its color and whatnot. We don't really care about the values of the ghost node block. The only thing we care about is, what a great observation. We don't care about anything about a ghost node block. So what I was thinking was like, we do need to modify the size, right? Something like set the size of the ghost node block to be 0, because currently whatever lives in memory at this point in time is like a mystery to us. Technically not a mystery. Technically, because this is our first allocation and the heap size was 0, it means that we're like allocating more stuff. Since this is the beginning of our program, the operating system already set the page that it's giving us to all zeros. So like technically, we know that everything here is zeros. I could be wrong. I think I'm definitely wrong. But like either way is just not good to rely on that. So I was thinking like, oh, we need to set the size to 0 and whatnot. But really, we don't care about the ghost node at all. The only thing we care about is the ghost node's left child being the root of the red-black tree. But that is what the red-black tree is in charge of, right? Because if you insert, and I guess, well, you do have to set the left child to be like, I have no left child. So ghost node block, and then set it to no child. Perfect. Yeah, I guess we actually did need to do that. Never mind. I swallow all the words I said. Arbitrary 13 expected expression. Oh yeah, because we have yet to create this. Perfect. So now that we have this, we're gonna create this. Let's see. You can replace align macro with this guy and non-alignment 1. It only works for powers of 2 though. Also add extra parentheses. Yeah. Oh, okay. So yeah, because currently that is, I think, the to-do. Fix this guy to be compatible with any alignment. I wanted to make it compatible with every single one, like something like that. But I guess, yeah, we could do it for powers of 2. Why not? Because that's what the X7 was there. It was for 8. Just fix it. Let's just update the comment and then just, yeah. So we have that there. Thank you very much, Andrew. Good modification. I think, let me check the parentheses. You're right. Yeah, it has the extra parentheses. So I think we should be fine. Um, Great. So here, going back to what we have, um, there we go. So we introduce the padding. We then allocate the ghost node. And after we allocate the ghost node, we set its left child to be null so that the red black tree can detect what's going on with this thing. Like so that the red black tree can say like, oh, there's nothing here, right? So I just need to set the root to something. Um, so we only care about the left child. Great. So once that's allocated, the ghost node is already here. I think this is all we need to do in our first insertion. So I'm just gonna include like, if true. I'm just gonna make this an if, right? So that this should be the to do, sort of make this, or like find a way to detect, to do, find a way to detect whether or not this is our first allocation, right? So if that's the case, blah, 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 we continue, and then we proceed to the normal malloc behavior. Ooh, let's see. Ooh, there's another chat message. I'm not sure why you would ever want non-power of two alignment also to check what it works. Yeah, so definitely, like I would never use a non-power of two alignment. I guess you're right? Like I'm making it general for no reason other than making it general. It is one of the evils of the evils I'm trying to abandon, or reducing the amount of unnecessary abstractions. Um, and like, there's no reason to think that somebody would want to do that. Let me actually. I'm intrigued by, even though we agree, I'm intrigued by what you shared, the Godbolt link. So I imagine it's gonna be some sort of compiled. Let's see, I'll explore and then uh, privacy policy. Why does Compiler Explorer need a privacy policy? Yeah, I guess I would read this yeah, if I'm intrigued about it. But like, anyways, doesn't matter. When you perform the alignment, yes. Oh, you mean to check that it works? Yeah. No, completely agree. No, I agree it works. I agree it works. I agree it works. If not, I would have asked like, wait, I think I disagree. But yeah, we agree on the fact that it works. And yeah, I mean, it's nice that you showed us that it compiles to the exact same thing. Pretty good. Um, See, you have another comment. By the way, just for your knowledge, modern allocators never use break and S break, but just mmap as a kernel. Wait, give me a second. Sorry, my earbuds are about to die. These are the only microphone I have. I need to take it off. Let's see. Modern allocators never use break and S break, but just mmap as a kernel interface because it gives better control over pages. There's some concurrency reason I don't recall precisely. That's interesting. Interesting. Okay. So they use mmap instead of break and sbreak. Pretty good, because thank you very much. I'm using break and sbreak mainly because that's like what the infrastructure provides, and also because I'm very ignorant with respect to memory allocators, in the sense that like the reason I'm doing this is because I wanted to learn. So that completely escaped my view. Damn. Yeah, I guess we can think of like how we would do it with mmap. For now, let's continue with the break and S break, just so because it's like what the infrastructure provides. But it would be a good exercise to see. See, it actually C and C++ different in Windows. Forgot to set second one. Um. Oh. You mean the this guy? Yeah. No, I see now. I see. Yeah. Let's see. If we add O3 to the compiler options, dash, will that change anything? Yeah. Okay. Oh wait. Oh. Oh, it changed the entire code. I was like, why is it all of a sudden completely different? Yeah. Yeah, Andre, realize, yeah. It was very weird. Okay. Perfect. We have it, and yes, it definitely works. We agree. All right. So thank you guys. Um let's see. So now that we allocate, do we agree this is all we need for the first allocation? I think yes. If somebody disagrees, uh, write in the chat and be like, Sharif, you missed this. For now, we can continue to, let's see. Also, if you switch to C++, you can see C++ name mangling in action. Function is called square and not just square as in C. Really? Let me take a quick look. C++, square. Oh, you're right. And if I do this in C, yeah, square. Huh, pretty good. Interesting. But yeah. So wait, name mangling. What, like, from what I understand, like, it's of course you cannot share names when it comes to like the actual construction of your executable. So you need to have like different names for each, and languages deal with this in like different ways. I imagine that since C++ supports overloading, the name mangling, like you mentioned, is there for that, right? Like the square is now named square int to differentiate the two objects. Is that what name mangling refers to? I'm just making sure. Like I think it is, but I don't want to assume it's the wrong thing and then be like, yeah, okay, yeah, perfect, pretty good. All right, so let's see. Here we are. Now we need to in this malloc call, and give me a second. I need to eat cornflakes. So we need to allocate space for the user's block, and the way we can do this. Okay, let me delete this line because this was written there previously. Oh, we have 7 viewers. Hello to the new viewers, to those that are tuning in. We're currently writing a memory allocator in C. We were working previously with red-black trees because they're going to be the underlying data structure that we're going to use to keep track of the free blocks that we have available. And right now we are starting with the nitty-gritty of like the actual memory allocator. So we're starting with our call to malloc, and yeah, that's what we're figuring out. So feel free to get in and out of the stream. I've been streaming for almost 6 hours now, 5 hours, something like that. So yeah, definitely like I'm gonna stay here until I think 6 p.m. I have to go at 6 p.m. Currently it's 4 p.m. where I am. So yeah, we have 2 hours, and if not, we can continue tomorrow. Hopefully not though. I wanna at least finish my lock. And yeah, that's all. Okay. I don't know why I gave such a prologue. So if this is our first allocation, we perform these steps. If this is not our first allocation, or like the things that happen after our first allocation, what do we want to do? We want to increase the size of the heap by whatever the user asks for if there is no free block, right? Expand heap. Otherwise, we can use the infrastructure of the red-black trees that we have already prepared in order to sort of work with everything. I have the static variable called the ghost node, but we cannot store in this tag. So instead, I think that we can simply use this to be the red-black tree. And so now that we store it there statically, as so that it sort of stays throughout, the multiple calls to our program. I know it's globals, but we, we need to store it for the entire cycle of the calls to malloc and all of that. It is really unfortunate. Unless maybe you guys have a different solution. I cannot really think of one. I think we really need that static variable to stay. But let me know. Because currently, because if it's not a static variable, then it's gonna be just something we put in the heap somewhere, and like that's not ideal. At least not because it's just a variable. So yeah, allocate the space for users block. So I think that one of the things that we need to do is we can grab the red black tree and we set its block to be the ghost node block. And I guess then that we don't need that variable name, we simply grab red black tree block and replace it sort of everywhere we need to. Then we grab this guy, we replace them, and there you go. Awesome. Okay, let's see. Can put it on the stack. Sure. Although my only fear. Okay. I guess I just made it static because I was like, yeah, I just want to use it in this file and I don't want it to be available anywhere else. But I guess if it's not declared in a header file, then there's really no way to access this, I assume. Correct me if I'm wrong. So I think, can we just do this and like, make it be there? Or let me know if what you're suggesting is different. I just wanted to put the static just so that it was clear, like, yeah, this is not used anywhere else. This is just here in this file. But yeah, let me know. Let's see. So we introduced this sbreak if there's no free block. So now we allocate space for the user's block. Okay. Instead of allocating space for the user's block, we need to do the following. Search tree for free block. So now we can do arbitrary. Oh, this is the moment where they all come together. Like this is the moment where everything combines. So we're gonna do arbitrary find with the red black tree that we have, and we're gonna pass in the size that the user wants. The size is gonna be the size of user data. Okay, not the size of the block itself, including the metadata. If we find something, it's gonna be like, best fit block. I'm gonna abbreviate this to block. That's gonna be the best fit block. And what we can do with it is, well, if the best fit block is different from a null heap pointer, that means we actually find a best fit block, we can give it to the user, right? And what we're gonna give to the user is not going to be the pointer to the block itself. It's gonna be the pointer to the user data section. So what we need to do is first convert this to a real C pointer, and then be very careful because we need to skip ahead a few bytes. How many? Well, the size of our header, right? So we first grab currently. Let me have this here on the side. Let me also hide this side panel because it looks kind of ugly. A block pointer or a heap pointer to a block is always going to point to this place. Let me reduce the width. It's always going to point to this place. And thus, if we pass that to the user, we're going to have a problem because the user starts to write stuff and it overwrites the metadata we're keeping track of. So what we need to do is we need to say, yes, the pointer to the block that you just found, but we need to skip header many bytes. So we just skip all of these bytes, and then we end up where? At the beginning of the user section. Okay. And so with that in mind, that is exactly what we return. Um, Let me make sure that we have that in mind. Yes, perfect. So that would be the case where life is simple and we actually found it inside the tree. Oh, wait, we have a new message in the chat. Oh, and another, whoa, Orion3037. Hello, and thank you for following. So now we have, how many? 15 followers. Dude, we're growing. Okay. Um, let's see. The allocator state usually goes in thread local storage, but yeah, it definitely needs to be a global due to how the malloc interface works. Yes, I agree. Alternatively, you need to pass the allocator every time. Yeah, really. So thread local storage. Really? I didn't know that. Um, Wait, sorry. How could you store it in thread local storage, like the state of malloc, given the fact that threads can share sort of the heap and etc. Um, and I think there is another message. Let's see, globals can put it on stack. Oh no, that was your message. Yeah, not suggesting you do it here if you're learning. Okay, perfect. Uh, Wait, but am I just confused? Like the allocator state going like in the thread local storage, which should be just the stack of the thread, rather than have a lock per thread. Yeah. Oh, okay. Okay. Sure. Makes sense. Okay. Well, I think if I fully understand it. So, because you would need the like every thread owns a slice of memory, and you can allocate in power. Oh, okay. Okay, yes. Yes, okay. This is perfect. Yeah. That makes a lot more sense. I thought that like the picture I had in my mind is we have the heap, sort of a universal heap, in which the threads simply are able to modify the same heap at the same time, like the same heap. So yes, you would need like locks, but then it would be like your fault as a programmer if you don't put the locks. And then in that case, we would need the universal state for all threads to access. So I was confused, like why would we keep the state thread local, given that like multiple threads are accessing the same heap? But if it is like the um yeah, if we give like a little piece or like we give each thread an allocator, then yeah. I don't know which one is the one that is used in real life. Which one is the like which model is the one that's used in real life? The sort of global heap or a per thread heap? Or like per thread, allocator. Let's see. Andrew says the only issue is with threads which die and don't clean up memory for themselves. So you need to read them. Yeah, for sure. Um, it is always a problem. Although, is there is this something that is usually done? Like, do languages do this? If you have a thread and the thread dies, do you help the programmer to simply? Oh well. I guess yeah. If it's a thread and it belonged to him. So what I was going to say is technically like you could blame that on the programmer and be like, dude, you didn't program your program correctly, so now you're like leaking memory and that's your fault. And then once the entire program comes to an end, the operating system is going to reclaim the resources. So it's in the end not our responsibility as the Malloc creators. Um, but I imagine it's different. I don't know. Let's see. Yeah, it opens a whole new can of worms. Okay. Definitely the per thread one. Oh, okay. So in real life, it's used the per thread one. I see. Um, there are whole allocators designed to make per thread allocation fast while keeping cross-thread the allocation not impossibly slow. For example, whoa. We have real projects here. Wait, let's take a look at guys. We are taking a detour. Wait, I know we're coding the memory allocator. Give me a second. We need to take a look at this. SN Malloc by Microsoft. SN Malloc is a high-performance allocator, as Malloc can be used directly in a project as a header-only C++ library. It can be LD preload and ML platforms, and there is a crate to use it from Rust. Key design features, let's just read the introduction. Memory that is freed by the same thread that allocated it does not require any synchronizing operations. Okay. Freeing memory in a different thread to initially allocated it does not take any locks and instead uses a novel message passing scheme to return the memory to the original allocator where it is recycled. This enables thousands of remote deallocations to be performed with only a single atomic operation, enabling great scaling with core count. Pretty good. The allocator uses large ranges of pages to reduce the amount of metadata required. The fast paths are highly optimized with just 2 branches on damn. On Linux compiled with okay. 2 branches. For now we have only 1. We're beating them now. Okay, never mind. The platform dependencies. Well, actually, no, we're not beating them because the whole red black tree has like thousands of ifs. So never mind what I said. The platform dependencies are abstracted away to enable porting to other platforms. As in Mallec's design is particularly well suited to the following 2 difficult scenarios. Allocations on one thread are freed by a different thread, and deallocations occur in large batches. Interesting. Pretty good. And there's another one? Brother, what are we talking about? There's 2 more. If you're curious about what else you can optimize for, Malloc optimizes for small and frequent allocs the allocs instead. The ones used by runtimes of programming. Yeah. Okay, let's take a look at that one. So, Tim, I assume it's the reason why people create allocators, right? Because, I mean, usually, like everything in a language, things are designed like multi-purpose. So if you really need something like this, 10,000 lines of code only, consistent data structures. Well, wait, I think let's do this. I'm gonna bookmark this so that I can be like me Malloc. I can visit them later after the stream. And let me take a look at Ez and Malloc. I need to also add it to my bookmarks. Bookmarked. Perfect. And then I saw there's a third one that Andrew shared. There is one in 200 lines. What? Wait, is it like was the goal to just make it really small in terms of lines? Or release fast optimization mode with multi-threading enabled? Is a singleton, it uses global state and only one. Each thread gets a separate free list. However, the data must be recoverable when the thread exits. We do not directly learn exits, so occasionally one thread must attempt to reclaim another thread's resources. Above a certain size, those allocations are memory mapped directly with no storage or allocation metadata. This works because the implementation refuses resizes that would move an allocation from small category to a large category or vice versa. Okay? Each allocator operation checks the thread identifier from a thread local variable to find out which metadata in the global state to access and attempts to grab its lock. Thread local variable to find out which metadata. Okay, this will usually succeed without contention unless another thread has been assigned with the same ID. Okay. In the case of such contention, the thread moves on to the next thread metadata slot and repeats the process of attempting to obtain the lock. By limiting the thread local metadata array to the same number as the CPU count, ensures that as threads are created and destroyed, they cycle through the full set of free lists. Interesting. It's created in Zig. I want to learn Zig. Like, I've heard so many things about Zig. The fact that this is written in around 200 lines of code is absolutely insane. And it's actually not 200 lines. It's like even less because they counted the comments in. This might as well be like 170 lines. That's absolutely insane. Wow. I need to find a project to learn Zig. I need to find a project to, I've heard of a lot of people that really like the language. Oh, we have 9 viewers. Oh, wait, We had 9 viewers per second, and that's the most viewers we've had in a single stream. That's great. Okay, we're breaking records today, actually. That's insane. Okay, let's see. Let's continue with this. What what were we doing? Oh yeah. So we have the situation where if we find a free block already with a red block tree, we're good. If we don't find one, then it means that we need to extend the heap, right? There is this sort of design question that I have been trying to see what is the most optimal thing. And it's the fact that the heap is, kind of like a vector, right? This is like instead of elements, you just have the bytes. And so when you reach the end of the heap and you need to expand it, you could apply the same heuristic as a vector where you where you instead of adding as many bytes as you need to expand the heap, like the exact size, you just like multiply the current size of the heap by like 1.2 or 1.3 or 2, right? So that now you have like a bunch of free space that you could eventually need in the future. And so you save all of these system calls that you potentially would make. And so that would be one, but then you're using more memory than you actually need. So I'm not sure which one is used in real life. My best guess, if I were to be guided by intuition, is that the heap doesn't follow the vector heuristic, that it instead just allocates whatever's necessary. Because since it's general purpose, you don't really know where this is going to run. So you don't know if there's like the extra memory that you're going to need. But it could be. Yes. It's so that you increase the heap and thus call a syscall. Yes, exactly. That's why I was thinking of like implementing that heuristic, because then you don't have to perform as many syscalls. But at the same time, even though you're using less memory, you are performing a lot of syscalls, but it's only bounded by the amount of concurrent allocations that you're going to have. Because once you like reach a point, then you're going to be able to satisfy yourself with whatever you free in your program. I'm just not sure. So currently we are. It really depends on the workload. Yeah. Okay, let's think about it this way. It really depends on the workload, but like we're just gonna make an arbitrary decision, right? Like we're just gonna decide. If you are worried about the speed of Malloc when it comes to allocations, which is already fast, right? Malloc is already fast, but if you're worried about it, then you yourself would guarantee that you first allocate a big object, then free it, and then be able to work with it. Like, I'm not sure if that's the right way to think about it. To be like, if a user is worrying about this, then probably they would have already accounted for this type of thing. Compared to the user that's trying to use Malloc and like now it doesn't work because it's occupying more memory than than it actually needs, then they can do anything in that case. Because the code that allocated all the things that Malloc needed is like completely gone. I guess we can just change it. Like we can just change it in the future. Consider that increasing the heap might result in copying everything over. So it can definitely be really slow if you keep busy. Ooh. That is a good consideration. So I guess so, yeah. So according to to StringMeat's comment, we may actually want to apply some sort of heuristic. I feel like both scenarios you could advocate for. We are going to choose the heuristic. We're going to choose some factor. If it doesn't work, if we see that it's like occupying too much memory and etc., right? If the infrastructure tells us, oh yeah, this is really slow, or not slow, or this is consuming a lot of memory, then we're gonna, kill it. Like, we're just gonna use the other approach. For now, let's do the heuristic. Okay. So if there is no free block, we expand the heap by how much? Well, we need to expand it by maybe some sort of factor. I guess it's better if we define set factor here in the header or something like that. Um, oh, we have another follower, Buzztronic. Thank you for following. Yay, we have 16 followers now. Yes. I think this is the stream where I've gotten the most amount of followers, with the exception of our first day, I think, in the series. So thank you guys. I'm glad that you're liking it. Um, Thank you for streaming C. Yeah, I mean, I'm more used to C++. There's like, so this is my first time sort of working in C, like the way it should be. And by that I mean like with the project that I want to create. Um, so yeah, thank you. We'll see. So we will see. Anyways, yeah, that was a real bad joke. Sorry, guys. If so, we were saying we could store here inside of our parameters of our program, sort of define something like expansion factor. So we expand by how much? We would like to expand by maybe 10%, 20%, 30%. We decide. So let's just do some number. I'm gonna say 35%. Not sure, right? Let's just put 35 and then we tweak it to see which one works and as we run the program. So what we have here is if there is no free block, expand the heap. By how much? Once again, 0.35 times the size of the heap, which would be the high byte. Oh, I guess we have a heap size function. Never mind. We increase it by that much, but it is also possible that 35% of the heap is not enough to accommodate the user's request. In that case, we simply take the max between this thing and the user's request, right? But be careful, because we not only need to expand the heap by the user's requested size, we need to expand it by the amount of bytes that it takes to store an entire block. Because the size the user specifies is only this much, right? We need to allocate this much, right? All of this stuff. So we need to account for that too. I think, I'm not sure, is there a library? Okay, what is the library in C++? Where is max declared in C++? Sorry, not C++, C. I'm just used to C++. Does not have a built-in max macro. If you try to use max, okay, let me. Oh, okay. So we just have to define the macros ourselves. That's fine. Could we just do it somewhere else? Okay, I'm just gonna worry about it later. Bro is code. Yeah. So what we have right now is sorry, I lost track of what we were doing. Yes, expanding the heap. Okay. So heap size returns a size t. So why are we left operand of comma operator has no effect? Oh yeah, okay. So we would need to extract the max between this this factor and the amount of memory we would actually need to allocate the block. It is technically possible that at the end of our memory, so I'm gonna write it down like here in the little canvas we have. At the end of our memory, maybe there's like a bunch of blocks that are allocated. Maybe this block is allocated, and maybe these blocks are allocated, right? And like all of this, right? But then there's like a little bit of memory left in the end. And in that case, if somebody calls Malloc, or Malloc, I guess, not Malloc, with a size that cannot be accommodated by this guy, then we would be expanding the entire heap by like whatever that size is, when we could technically be using whatever is left here and then add to it whatever it needs to succeed. Although I feel it complicates our program by a lot, because we're not keeping track of where the last block is. And I mean, we could do that. And actually, now that I'm thinking about it, I don't even know what I'm saying. Like, we do know what the last block is. We go to the last part of the heap, and since blocks have this size at the end, we're gonna know what the size of that block is, and then we can use it for our advantage. To our advantage, sorry. Okay, so this is getting a lot more complicated than I thought. Let me stop for a second, because I think I'm considering too many things at the same time, and that is kind of ruining like the design. Like, we have to be really careful. So the way we want to think of memory, right, is when like at every point in time, the entire sort of memory stream, the entire heap, is going to be covered by blocks. So maybe this is a block of size 12. Imagine each of these squares is 4 bytes. We have this thing. Anyone who uses a white theme whiteboard is cooked. Okay, all right, buddy. Like, what? You know, it's a little technique only the pros know. The guys, what side are you on? Are you on, bro? Are you, bro? Andrew replies with real. Okay, yeah. Anyways. I'll consider changing the. Okay. If your room is well lit, maybe it isn't as bad. Yeah. Currently, it's kind of well lit, so we can live with it. Maybe at night. Maybe at night it creates like strain in the eyes. But you know, it is the life we have, and this is the default theme, and I just didn't change it ever. So yeah. So currently, our current memory model is we're going to have blocks covering everything. And by that, I mean that the white space that we're not using is just going to be a free block. So we are always going to be able to tell what the last block is by going to the last address of the heap and looking at this size member variable. We have to have in mind that actually we don't need to have anything in mind. Yeah, we can just do that. So once we do that, we can now know how much size we actually need extra. So we will need to compute that number. You're 32, sort of needed needed space, right? So the amount of needed space that we're going to require, needed space, okay, is going to be first the size of an entire block, so size of block header plus the size that the user is telling me they need, plus the size of the block footer, right? So we agree on this. This is however many bytes we need of space. But we could subtract from this the amount of size that we have free at the end, if any. So now we can... Ooh, never mind. Never mind. Okay. I may be exaggerating, but I don't think we can use the last block. And the reason is very simple. There is no way currently in our current design for us to know whether or not this is free or allocated. You may be saying, Sharif, what do you mean? Then how is your Malloc working at all? Right? It is working because the differentiation, the factor that differentiates this is like whether or not we know a block is free or allocated is whether or not it is in the red black tree or not. For now, we've only needed to differentiate allocated and freed blocks just for the sake of providing something to the user, so that thought has been fine. Now that we need to inspect the last block, we need to know whether it's free or allocated, but we cannot check if it's in the red black tree without incurring into a login search and also without modifying a bunch of things. We could, in order to implement this little sort of optimization when it comes to space, simply store a bit that indicates whether or not something is allocated or freed. Okay. Let me see this. Do you know about wait, if your room is well lit, maybe okay, yeah. Do you know about intrusive and extrusive data structures? Not by those names. Maybe it's a concept I know, but I don't remember the intrusive and extrusive names. Oh wait, I pinned something. Whoa. How do I unpin a message? Sorry, I clicked it by accident. Where is the pin message? Guys, I don't know how to use Twitch that well. Oh, I see it. Unpin this message. Yay. So let's see. Also, is memory contiguous? Okay, yeah. Also, is memory contiguous between blocks, like the user data part? Not sure what you mean. Like the user data is indeed a contiguous block of memory. That's what we're giving to the user, and then they can just use it. I'm not sure if that's what you mean, though. Let's see. Andrew says, okay, RB tree, and then you pass the templated type versus struct t, and then RB tree, node tree, and then other fields. No, I haven't seen sort of this difference. I usually always use the first one, which I guess it's extrusive according to what you mean, to what you say. So yeah. I'm not sure. Like, what is the difference? Like, why are they used? We should look this up, but I don't want to bore you guys with me trying to learn like a bunch of stuff. Although, never mind. Extrusive versus intrusive. Intrusive? Yeah, intrusive data structures. Let's see. Let's enter here. Yes, that's right. Is there a difference between intrusive and intrusive list when the member type is struct? Well, I feel that's for like the list itself. There you go. I've seen the term intrusive used to describe data structure like lists and stacks, but what does that mean? Okay. An intrusive data structure is one that requires help from the elements it intends to store in order to store them. Okay. That makes sense, I guess. So like if you have a linked list, whenever you store the members, like the next pointer, previous pointer, etc., into the node rather than relying on a global class. Maybe? I don't know. Let's see. Let's keep reading. Let me reword it. When you put something into that data structure, that something becomes aware of the fact that it is in that data structure in some way. Adding the element to the data structure changes the element. For instance, you can build a non-intrusive binary tree where each node have a reference to the left and right subtrees and a reference to the element value of that node. Or you can build an intrusive one where the references to those subtrees are embedded into the value itself. Oh no, so it's different to what I was saying. Okay, an example, it is kind of similar, I guess. An example of an intrusive data structure would be an ordered list of elements that are mutable. If the element changes, the list needs to be reordered, so the list object has to intrude on the privacy of the elements in order to get their cooperation, i.e., the element has to know about the list it's in and inform it of changes. ORM systems usually revolve around intrusive data structures to minimize iteration over large lists of objects. For instance, if you retrieve a list of all the employees in the database, then change the name of one of them and want to save it back to the database, the intrusive list of employees would be told when the employee object changed because that object knows which list it's in. A non-intrusive list would not be told and would have to figure out what changed and how it changed by itself. Okay, makes sense. So from your whiteboard, it seems that user data is part of the block itself. So if you allocate multiple blocks, the user data parts of two consecutive blocks are now contiguous. Okay. I see what you mean now, Strictate. I realize what your question is now. Yes, user data is part of every block itself. So kind of see what you mean now with intrusive versus extrusive question mark. Like, is this connected to it? The fact that we could just have like a completely different section of memory that just stores all of user data, right? And then we just store like references to the user data and then point them all the way over here. So user data is like, completely oblivious and like it just lives in that one guy. And instead, maybe. But yeah, no, currently it is designed so that, oh no, this guy's staying there. Okay. Currently, it is designed so that user data is part of every block. The thing is, like, we could do it in this way, but, and let me know if this isn't true. I feel I would encounter the problem that if it was a contiguous section, then you could outgrow the amount of memory that you have, like, right? Because if we divide the amount of memory we have, we allocate something somewhere else. Well, I guess it's not a real concern. Well, maybe the fact that we introduce overhead by storing a pointer to that instead of storing the user data itself. But I guess that would be combated by... It could be another possible design, actually. And it might be a pretty good one. My only problem would be what happens when you have like a whole sort of section that you're going to dedicate to user data and you outgrow that section. Then you would need to sort of either move it somewhere else, or but you still do that with the current design. Um, I guess that would actually be a little bit of a better design. Unless the user data memory is contiguous across blocks, you can't reuse the space at the end. Wait, why? What do you mean? Why wouldn't we be able to do it? Because this block is like the space that we reuse at the end is a free block, or like the condition to reuse it would be for this to be a free block. So if it is a free block, we wouldn't be intruding into anything that the user has put in there because the user freed it. If it is a block that like we gave to the user and the user is only using this much, then of course like we're not gonna do that. But if it's completely free, we should be able to, no? Or is there something I'm missing? In the meantime, let's eat some frosted flakes. Oh no, now I realize. Okay, okay. Wait, you were trying to subtract the unused space at the end of the block from the needed space. Oh, you mean here? Okay, let's see. Yes. Okay, so the idea, like what I was mentioning is if memory currently looks like this, and this is a 12 byte block that is just not being used, that is, it's freed, and then the user asks for, say, a 24 byte block, then according to the memory layout, we don't have anything to suffice that request, which means we would need to expand the heap. We would naively expand it by 24, so that would be 6 blocks, assuming each block is a 4 byte block, right? But we could make use of this last block at the end that is free, and instead of allocating like 6 more boxes, only allocate these last these 3. Oh wait, you posted a comment. Maybe that explains what you're saying. But the first 12 and the second 12 would not be contiguous, and the user expects it. Yes, of course. Like we expand the heap by this much, right? And then merge those 2 blocks, right? Now we need to update the metadata of this block to be 24, including the new space that has been allocated here. Whatever the size was here at the footer, we need to remove it and now include it at the end of this one. And then we get like a whole, like the section that the user needed. Oh, that makes sense. Okay, perfect. Okay, so we agree. And that's sort of what I was trying to do. Yeah, I maybe didn't explain myself very well on that one. So yeah, that was all. So let's see how it turns out. everything everything bad, it starts like that. No, it's like let's just make it the experiment and see how it turns out, and then it ends up being total hell. Or yeah, I had someone on my internship be like, oh no, just like code something really fast and see how it turns out. So I didn't really pay attention to the code I was writing because I was like, yeah, this is just a test, and this is just like to see how it works out. And then they just ended up using that code. So it's I would have written it differently if I knew that they were actually going to implement it. But yeah, so let's see how it turns out. Anyways, so from what we need, which is header, size, footer, we're going to subtract the size of the block that we have at the end, if that block is free. And this is where the problem begins, right? So if last block is free, then we can do this. The problem is, how do we know if the last block is free? Once again, this introduces what I was mentioning, and it's the fact that we are not keeping track of who is free and who isn't. The way we track that is we implicitly do so through the red black tree. If you're accessible through the red black tree, then you're free. If you're not, then you're allocated. And for now that has worked, but now that we actually need to detect that in a block, we need to keep track of it. So let's go back to the code and try and see, I think, emphasis on the think, we are able to implement this. How, you're asking? Don't worry. Don't worry about it. We're gonna figure it out. So what I'm proposing is this. We're currently using the least significant bit of the parent field, so of this field, to store the color. So the way it's working right now is assume that like a heap pointer is only 1 byte long instead of 4 bytes long. So we have 1, 2, 3, 4, 5, 6, 7, 8. Maybe the parent pointer, maybe it's pointing to something like this, right? Some heap offset. We know nonetheless that since the parent pointer is a heap pointer to another block, and all blocks are 8 byte aligned, these 3 least significant bits are just gonna be always 0 because they have to be 8 byte aligned. And this was something that the first chatter we ever had pointed out to me when it was only him and I. And it is a great idea. I hadn't really thought of it. So it means that you get 3 bits of storage free. Currently, we're using the least significant one to store the color. And I think we can simply use the second least significant one to store the whether or not it's allocated or free. And I think with that, seems like a good plan. We're not using more memory. We're not doing anything bad. So let's get to it. Extern, bool, bk, let's just call it free, right? Is it free? And well, block is free. I don't want to confuse it with like free the block. And you need to pass to me a block. Okay, so is the block free? Which block? Well, the one I'm going to pass to you. And we also have to be able to modify that bit and say, well, set the free bit to the block I'm passing you and the value that I'm also passing you. So is free. All right. It says that identifier bool is undefined, so I think we can just include std bool over here. H. Perfect. And now when we go to our implementation over here, we can simply say, well, block, is it free? You're going to pass me the block that you want to know this information from. And what I'm going to return to you is, I'm going to convert this to an actual C pointer. Then we're going to access the mysterious field that stores the parent and the color. And we're going to want to AND this, or mask this with 2. Right? Because we want to, 2 in the end is just like 1, 2, 3, 4, 5, 6, 7, 8. This is 1 here. So that's the one we extract. And then we are happy ever after. Okay? And once that happens, we need to return it. And I assume C is going to make the conversion from if it's a 0 false and it's a true, and if it's a 1 true. So here, now we can grab void and say, okay, block, set the is free bit. And to whom? Well, to the block that I'm giving you, and set it please to the following value, right? And what we want to do is we're going to say, well, the block pointer, right, convert this to an actual C pointer so that we can access the information. We're going to access this weird esoteric field. And what we want to do is we want to add this with who? With what? So first, we need to erase the value that's currently there. Yeah, so in order to do that, we would need to mask with once everywhere, except for that guy. So we simply negate x2, and this is 2 underscores. And then we're going to set that thing to be what we want. So we change this to a block pointer. And then at PC, we OR this with whatever we have at is free. Just shifted 1 bit to the left. And I think that should be it. Right? Strignit says, oh wait, oh classic. Strignit says, you can use the 0b notation to write masks in binary for clarity. Oh, okay. So I imagine that we can just do something like 0, 1, 0b. But I feel like is this the right way? I'm not sure how to use it. Okay, wait. How to use binary number in C. Write in binary number system in C. Oh, wait, sorry, I'm stupid. This is a prefix, just like the 0x prefix. Sorry about that. Okay. Perfect. My only problem with this is the fact that like maybe well actually no I think we're gonna be fine, right? 0b1 0. Although we've been using the X mask all along and we use it for a long value since the binary one is a little bit difficult to work with when you have like 32 bits to set. So I think just for the sake of staying consistent, I'm going to stay with the hex values, if that's okay. Unless you guys like consider it to be like a really strong decision that we should just change everything to binary. Let's see. I would write on line 58 just for symmetry with the next line. See, I'm not sure if I would prefer that. Because even though it's symmetry, like now it's even less clear to me. Like I feel like you can just visualize what the value, what the hex is. Maybe this is the fact that I just like the hexes. Like I'm really biased. But yeah, I think once again, like here, right, we sort of used it, and I guess, well, I guess this is just like right the negation of 1. So I guess we don't really need the hex. So actually yeah, we may just do that. let's apply Strickneat's recommendation, where you can just do 1, right? And this with, sorry, it was the negation of 1, yeah. So Well, now we're entering the negation space again. Oh yes, Nick Borsa. Thank you, thank you, thank you, thank you. Now that changes. Yeah, yeah. Now that changes how everything is done. I guess that's what you meant when you said you need to update BK parent. Yeah, thank you so much. Thank you so much. Yeah, that's true. We just need to update this. Don't listen to this troll. No, no. It is true. It is true because the parent is only returning like the rest except for the least significant bit. But now that we're storing the free bit, we need to account for the fact that like the free bit is now there. So we don't want to filter it into the parent. So we need to do this. Yeah, I agree. I agree. I agree. 0B11. Okay. All right. All right. All right. It is a matter of like understanding of like sorry, not understanding of like what we are used to. I am willing to concede on that. It is a little bit clearer, I would say. It is a little bit, but only a little bit. Yeah, 0B01. And then maybe this one we can change to 0B01. And then 2. And 2. And then just 0B10. And then this guy is just 0B10. We select the first bit. And then we just transform this guy to the left, and that should be fine. Next, so you say not 3 bits, just 2. If 3 bits, it will be 7. Yes, yes, completely agree. Hex 3 would be 1-1, so it would be yeah. So I understood the message. Fortunately, thankfully. Let's see. If you're okay with your C code being non-entirely portable, you can use bit fields, and it would be even better. I feel we're fine with the current way it's done, and also we have already battled with bit fields. We actually did so in the last, like yesterday. Neg Vorsa was there, and the fight with bit fields was not at all good, mainly because of how C truncates the values. So whenever we try to set the parent, right? We could do something like, arrow parent and then equal to whatever the new parent is. The problem is that C doesn't truncate the least significant bits. It truncates the most significant bits. So then we get rid of information that we don't know. Because we do know that the 3 least significant bits are 0. So we can do whatever we want with those least significant ones. But when C truncates values to fit them into the bit field, it gets rid of the ones in the front. So the most significant ones, since it tries to fit it into a 31-bit space. And we really like tried to do it, and we ended up arriving at this solution. It was a huge issue. So now, yeah, that's why all of the functions are like this. It's not just like, oh, I wanted it to play with hexes, but yeah. I think everything is fine now. I think the last thing we need to do is, let's see, set this and then OR this with okay, yeah. I changed the hexes, and now I removed some negations that I shouldn't have removed. Let me go back to hexes and remove accordingly. Okay, this is the same as the negation of 1. This guy is the same as... Yeah, I think I deleted this guy by accident. Yeah, and this should be 0B01. This guy, merged with 01. BK color. And to set the color, we can just OR this with the color. That's completely fine. To set the free one, we need to end this with 1, 0. So we're selecting the second one. And here we need to get rid of, let me see, what was it? 0x2, so that's 1, 0. And then here we need to shift to the left by 1. Perfect. And now we need to go to the parent and find this guy because the color was not bad. Oh, new message. 0B11. Yeah. Yeah, you're right. I was about to miss it. This guy needs to change. And yeah, okay, I feel this is the final version. Perfect. So, okay. Also, it's 2 a.m. here. He goes to sleep. 2 a.m. Where are you? Oh my god. 2 a.m. where? Oh, I imagine you're in Europe. We have 9 hours of difference, 9 versus 10 hours of difference. Yeah, so I imagine, yeah, and more with like the Iberic coast between Spain, Portugal, Italy. Okay, so I imagine that, Andrew, you're more in like Eastern Europe because you have 1 more hour than Strychnine. So yeah, guys, thank you. Like Strychnine, thank you for hanging around and for helping so much. I don't know. I'm not sure, Andrew, you're going to bed. If you're going to bed, let me know. But thank you so much, guys. I'm sorry it's 2 a.m. there. It's definitely really late. So, yeah, have a good sleep. Have a good sleep. And thank you so much for helping me. I'll probably be streaming, what, for the weekdays at like 6:30 of my time. So that's going to be 3 a.m. and 4 a.m. respectively for you guys, but I usually stay until midnight. And midnight would be 10 a.m. for Andrew and 9 a.m. for you, Street Need. So I don't know. Yeah, if you guys can ever tune in, if you catch me at some point in time, don't hesitate to do so. But yeah, good night. Good night. Thank you very much. And Nick Vorsa, you're saying set to 0 to 1 1 in the set parent. Yeah. See, okay, that's right. Thank you, Nick Vorsa. Yeah. So we get rid of this. We continue here. Yes, we set the color. The color, nothing changes. To know whether or not it's free, we select the second one. And here we say, okay, once everywhere else, except for the place I want to occupy. Right? Yes. And then we set this here. Okay, we're fine. We're fine this way. So now we have the functions to interact with whether or not something is free or not. What? Function definition is not there. Oh, set is free. Okay. So the only place, 958, 0B10. Oh my god. Okay, this change to the binaries, starting to doubt it. But yeah, I think that's the last one. Dude, what would we do without Negvorsa? I feel like because you've always pointed out like the little syntax mistakes that are very crucial. So yeah. You know how like usually languages are compiled on top of each other? That is like the C compiler was created with a version of C that was more primitive, and then it's a recursive sort of relation where you get to like the first compilers ever, which were like assembly and so on. And who writes the assembly? Those were the humans. Negvorsa was like the original compiler, bro. Like it's Very good. Thank you, Nick Morza. Okay. Uh, let's continue here. And this similar for Strigan and Andrew, like pretty good observations. Um, let's see. Now that we have this, I think we can go to our B tree and actually implement those changes. Whenever we insert something into our red black tree, it means that it has been that it is free, right? So we just have to make sure that whenever we insert it, we say, well, blocks that is free for new node to true. Well, it's free now because you inserted it into the free tree. And now in remove, we need to set it to allocated. So every time where we want to delete something, and this is the part that is going to matters in the future. So if deleting the only node left, right? So that's an example where we need to set is free. We need to set it for the block, and we need to set it to true. It is free. Let's see if the array is different from null pointer, then we swap blocks. This doesn't seem to do anything. Getting rid of the double black. This is the place where we're gonna have, okay, case one. The block is red. And so I think I'm just gonna pull up the, let me change, there you go. I'm just going to pull up the previous code so that we are able to identify, like, you know, the deletes. So wherever there's a delete, it means that we were intending for this to get out of the tree. So bk set is free. We're gonna set this block to true. It is now free. And in fact, I think, no, actually false. When we remove it from the tree of free blocks, then it becomes an unallocated block. Sorry about that. Okay, block, and then true, and then false over here. And then, ooh, I lost track. Okay, that's case one. So where do we use delete? We also use it down here inside of case three. Inside of case three, here in the is db nil. So if it is nil, we want to delete the node. So we say, well, that block set that is free to be true. Now we're gonna have block and then false, actually false. All right, perfect. Now we continue. And then this delete, we have it already, is the case 3 one. Next one is present in case 6. Okay, so case 6, here we're going to do this. And then what we're going to do is we're going to say, well, set the node to free. Nope, you're going to allocate it, so false. Perfect. And then we set the color of the far nephew, and that's it. That's all we have. Those three. So once again, deleting the only node left, which is the first one. Here we set it free. Right. Then we delete in case 1, which is exactly what we do. Then we delete in case 3, which is exactly what we do. And then we delete in case 6 over here, which is exactly what we do. And then we go back. Yeah, okay, perfect. We can be more than, we can be tranquil on the fact that nothing bad is going to happen. So now that we know that, now we're going to be able to apply the optimization. Oh my God. This whole journey is just us going on like the biggest tangents ever. And yeah, so the needed space is going to be the space for the new block that you're going to have minus whatever space is available at the end. So we're going to look at the high mem heap high. So that's going to be the high bit. And we're going to take a look at this. Okay, so if we are in the last byte, right? If we're like, if our memory, what about insert? Are those free? So in insert, we already take care of that because when we insert, we need to set it to free, but there's no special case, so we just, we set it to free. Oh, I guess I'm dumb, right? Yeah, I'm really stupid. Because we don't really need to do this in every single case. We simply do it at the beginning, right? Whatever block you pass me, I know that it's eventually going to be deleted. I don't care about the way it does get deleted. So, ooh, okay. Here we have okay, we have a lot of trouble introducing this because, yeah, no. I think we're fine. Yeah, perfect. So remove is there, and then in insert, like whenever we insert something, like we know it's going to be inserted, so we just simply set it to true, and then it's free now. So yeah, we're fine. If the last block is free, what we're going to do is we're going to grab the last byte of the heap. So now don't think of these as like 4 byte blocks, just think of them as 1 byte blocks. So we are here. Oh, sorry. We are here. So it means that we need to go back by, because remember that the last 4 bytes are going to be the size. So we need to go back by 3 bytes. So, okay, prepare for hell. Memory heap high. We're gonna convert this to a char star. And then to this guy, we need huge parentheses around this. To this guy, we need to subtract 3 to access the size. Now, once we have the size, this gets converted to a UN32, right? UN32T. And actually, we would need to subtract by size of UN32T plus 1, right? So we get the size of this block, and after we do so, we know what the size is. We now know that, okay, so what I'm saying right now is something like this, right? Where if we have the board over here, perfect. So the size of our block is gonna be stored, why is it so sweet? Okay, it's gonna be stored also at the end. So whenever we expand, we need to take into account that this size is no longer going to be there when we expand. So we also need to add the 4 bytes that this thing gives us. And so in needed space, we not only claim the size that's available, which is this one, the user space size, we also claim the size of this guy, the footer. And so we add to this we add the size of the footer, block footer. But it is added as one of the things we can subtract, which means that it goes inside this parentheses. Gosh, this is really, really... It smells fishy. It's like not... it's like one of those things that we're like, yeah, I think it would be advised to make separate variables. Let's do that, yeah. Block size. So the block size is going to be size of block header plus the size the user is requesting plus the size of the block footer. right? So it'll be this guy, the block size. Then from block size, we need to extract, okay, we need to extract the amount of what? The amount of extra space. So yes, we need alignment for this block, but it is possible that like after we subtract in the space that was free before, everything just happens to align. So we perform the alignment, but at the end of the entire thing. So yeah, that's it. Let's add that as a to do. Add alignment. Oh wait, somebody's calling me. Okay. Oh no. Okay. Seems like, yeah, I will have to go soon. I think by around 5:40. But it's okay. Let's continue. Let's continue. Add alignment. Add alignment. So to do, we need to add alignment. Here we have our block size, and apart from the block size, we need a variable for like the amount of space that we can reuse, reusable space. And that's going to be the size of the last block. So size last block. And that's going to be equal to, we're going to go to the end. So it's this expression, right? Yeah. So we go to the latest, to the highest byte of the heap. Then we subtract from it the amount of bytes present in a uint32, and then we add 1 because we were already sort of standing at that byte. Yeah, so this should be fine. No need to make this cast. Oh wait, no, there is a need to. What is the problem? Oh yeah. This needs to be a uint32 pointer. Yeah. And then here, this much. Yes, we could do block footer. I suppose, yeah. Let's just do that. So yeah, I mean, because the footer is only a uint32, so it would be interchangeable, but you're right. It's more versatile if we just do it that way. Reusable space. Right. I think we can just access this as the footer, right? And then just be like, oh, this is a block footer pointer. And then just make it this way. And then over here for reusable space, okay, last block. Last block block footer is equal to this thing. So character star and then heap high and then minus the size of the block footer and then +1. I think we are good to go, question mark? Is this enough? So it's gonna tell me that it's a char pointer. Yeah, so we simply need to convert it over here. Block footer and star. All right, wait, we have a new chatter. Stop using AI. Let's go. So you're coding a memory allocator from memory. How will you allocate that? So we are, well, okay, do you mean like we're using variables and so we are making use of memory, which is like circular? If that's the case, if oh okay, yeah, because I was like, the other thing is you meant that as a joke. It's like we're coding the memory allocator from memory. But yeah, I mean, Yeah, I mean, we went through the entire design like a week ago, and I've tried to not look at any sort of reference from memory allocator. We sort of need to know what the allocator needs to do, and we've been designing one from scratch, total scratch, including the design. Um, yeah, I just watched like a single lecture on like like how the memory allocator, the basic things you need to know, like the heap and all of that. And then after that we just began. Um Currently we are trying to write the main function because we've spent all of this time writing a lot of code for other things. In this case, a red black tree for um, to use as a data structure to store our free blocks. And yeah, we're doing an optimization right now. Like not an optimization, well, yeah, I guess so, to reuse space. And it's that if the last block in the heap is is free, and we need to expand the heap, we don't really need to expand it by whatever amount we were supposed to expand it by. We can just reuse the space that's already free at the end and then add a little nudge. So that's what we're doing right now. And currently that looks like this. So, oh, sorry. I'm going to close this here. Okay, we're going to use reusable space. And then what we're going to do is we need to access the size of the last block, right? And not only are we going to do this, but from the block size that we need, we're going to, well, actually, no, reusable space, sorry. This is going to be the size of the user data plus the size of the footer. I don't know why I am making these mistakes. Okay, perfect. Awesome. So now the needed space is going to be the block size, or whatever we need to allocate, minus the reusable space that we can make use of. Nick Vorsa, you were completely right. This was the right call. Separating everything into variables is definitely the thing we wanted to do. So perfect. Let's see. Stop using AI says, "What is your perfect Sunday?" I have to be completely honest. I have never really had a Sunday. Uh, do you mean like is it the ice cream? Like maybe I've had one, but not under the Sunday name. What is like Sunday? Sunday? Yeah, I've never really had one, which is really sad. Like this is one of the things that I would love um to eat. I've had like milkshakes made with ice cream, but I'm not sure if it counts like this. Um yeah. This looks very delicious. I will at some point in time try one. Um I definitely eat ice cream though. So yeah. I don't know. I feel like I would like this one. This one, like if it is like a milkshake that has cookies and cream in it, and then like all of the chocolate on top, it would be absolute like no madness for me. So I'll be the answer to your question. Hopefully that answers that. So let's see. All right. Um, I think we're good. I think we're good to go. I think this is the needed space, and we can simply grab needed space and substitute it here. Remember that this only happens if the last block is free. So what we have to do is to figure that out. We take a look at the last block's footer, then we go back to get its header, right? Header, 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 right? Like last block's header. And the way we do it is we take a block header pointer. And where is this pointer going to take place? It is going to take place from the last byte of the heap. We need to subtract the size of not only the footer, right? But we also need to subtract the size of whatever the footer said the size of the user section is, size. And then we add 1. Perfect. So that should be the header. Should be the header. To do test, this is actually correct pointer arithmetic, because if it's very possible it's not. So we need to test that. Okay, now we are going to say, we're going to say that to detect whether or not this block is free, we simply say if the last block header tells us that this is free, so block is free, block is free, and then actually I do not need this, I need the heap pointer instead. Sorry, here. I need a, no. Okay, that's what, and then heap pointer t. Okay, let me pause because I think I'm not doing a great job here. Wait, don't you think that not knowing Sunday is indicative of a deeper? Probably, yeah. Unfortunately, but I mean, if you meant ice cream, then I have consumed ice cream before. Yeah, I didn't get +1 in the first place. Oh, I think it's. Let me know if I'm just hallucinating stuff. But if we have like the last, I don't know, 6 bytes, like this one, 2, 3, 4, 5, and then 6. I think that, let's see, stroke width. I think that when we access memheap high, we return the address of the last heap byte, so we would be placed here. Then when we go back by block footer, block footer is only 4 bytes long. So we would go 1, 2, 3, and then 4. But the footer starts here. So we're like 1 off. So then we just need to add 1 to go back to where the footer actually starts. I think that's the reasoning. It's just because we start inside the footer rather than here. But let me know if that's not the case. Yeah, I think it's fine. Not sure. But yeah, heap pointer. We need to point to the last one. Let's see. Stop using it. How regularly can we go get ice? Regularly, I honestly haven't eaten ice cream in like ice cream, like what we call ice cream. Maybe like what, 7 months. It's a long time. It's been a long time. Can we go get ice cream? Switch the stream to our own. I'm not sure if like the people in the channel would be very interested in like watching me go get ice cream. It is definitely a different audience for what a memory allocator requires. So I don't know. It's also, stop using it. Are you like, where are you from? Like, are you are you proposing this seriously? Maybe somebody in the chat is living near you and you can go get ice cream. But yeah, I don't know. From the US. Oh, great. Are you like in, maybe you're in California, since a lot of people in tech are also in California? Um, but yeah, not sure. Connecticut? Connecticut. Wait a minute. Wait. Connecticut. Interesting. Very good. So it's currently what, like 8 p.m. where you are? Hmm. 8:35. I know, already eating homemade cakes with tea. Damn. Wow. Pretty good. It's a perfect time to get ice cream. Yeah. I mean, it's like a little. Well, I guess it's summer, right? So the sun hasn't set yet. Um, X-Men Runner 383. Oh, hello. Welcome to the chat. Yeah, I saw it. Welcome. We're writing a memory allocator from scratch. So pretty good. Um, so why are we? So I guess we have to go get ice cream at some point in time. Um, maybe you can go get ice cream. I'm not in Connecticut, so cannot really go get ice cream with you guys. But yeah, um, what was I doing? 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 Um. Oh, here it is. Here it is. Is bread good though? What do you mean is bread good though? Like, we're eating frosted flakes. Mm, agreed. Bread is good. I think we simply need to subtract. Oh my god! Wait. Hmm. Let me think. Yeah, I think if we subtract the mem heap low, um, from this entire thing, we're going to be okay because we can simply convert this to a uint pointer. Yeah, I know it's getting really long, the expression, and I know Negvorz is gonna kill me. Give me 1 second. Like, I'll fix it in like like a few minutes. So now we want to extract the heap pointer for these guys. So now that difference, we convert it to a heap pointer. Awesome. X-Men Runner 383. Oh, thank you for following. Yay, we have 18 followers. Guys, we're growing. Damn. We started the stream with, dude, 11 followers. Like, we almost doubled by now. That's crazy. Um, yeah. So, pretty good. Pretty good. Um, okay. 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 Let's walk through this. Guys. We let's see. We are going to grab. Okay, okay. Let's read this like a children's book, because currently we are like very, very you know a little bit uncomfortable with this. So we grab the mem heap high, this one. We go back the amount of steps of the footer. So I would say 4. So 1, 2, 3, and 4. We're here. Now we need to add 1 to that to end up where the footer actually is. So that's the +1 we see there, right? And then we need to go back by the amount that the size is indicating. So suppose the user section was, I don't know, I'm gonna put this 2, 3, 4. Yeah, um, I think, it's 5:40. I think I have to go really soon because I have a compromise. I have a compromise with some friends, and we need to. Yeah, I need to get up. But okay, let's extend it to 5:45. 5:45. 5:45. Okay, we're at the footer, right? At least let's finish this section. We're at the footer, and suppose the user section is these many bytes, so 4 bytes, right? Then after that, we need to. The footer is gonna tell us, oh, the size of the user section is 4. So then we go back 4. 1, 2, 3, 4. We are at the beginning of user section at this point in time, right? Then after that, if this is the start of user section, then we need to, oh, that was the error. We need to actually subtract the size of the block header so that we end up at the beginning of the block, right? So that would be like 20 bytes. And then we get to the header. And after that's done, we subtract this from the heap low to get the actual pointer to the thing, and then we're done. Okay. Let's see. A lot of messages in chat. Let's see. I must let you grow. Okay. Thank you. Also, I am 3D modeling while doing this. Yo, congratulations. So I'm working slow now. All right. Children's book. Yay. Oh, I imagine this is with respect to the comment of me saying that we were going to do that. Now read for me. You're welcome. Okay. Code and memory allocated from scratch and scratch when. That's actually, it could be a genuine challenge. I'm not sure if I'm too interested in that. Code and memory allocated from scratch and scratch while getting scratch when. Whoa, 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 whoa. Coding and memory allocated from scratch and scratch while getting scratch while scratching yourself when. Not sure. That's going to be a little bit far into the future. But yeah. So let's see. That is a lost block. And Nick Vor says, why don't you use size footer? So you mean, what do you mean by size footer? Because currently we're using the size of the block footer over here. Do you mean to use the pointer at which the footer starts? Ignore that question. Oh, okay. Although no, genuinely, I think it's better if we just use the pointer to the footer, right? Like whether you intended it or not, you just proposed something that will allow us to simplify things. So last block footer. So yeah, so we part from the last block's footer, then we subtract the size of the block, then we go back by the header, and then we end up where we want. Perfect, that's the last block. So if the last block is free, then we perform all of this, right? And then we grab these guys and we put them here. And we add the alignment. So, okay, block size is that. And the reusable space is the same as always. And then the needed space is this much. So I guess that for needed space, we're always going to need the amount of space. Ooh, why is it in minus? We're always going to need the amount of space. So needed space. We always know that we're going to need at most block size much space, right? And here, in the case the last block is free, we're simply going to say, well, from needed space, subtract whatever we now know we can reuse, right? And then here at the end, we can simply say, oh, okay, I guess so. Block size, it's over here. And then we, reusable space we have. So at the end, we have this. And we have memory as break. We need to pick the maximum between this guy and this guy. So, 32, size to expansion size. Okay, guys, I really think I need to go. I really think I need to go. And okay, give me a second. I'm gonna mute myself first. Hello. There you go. Okay, guys. I think, um, as I said, I really have to go at 5:45. It's already 5:46, but we are just so close, so close. Okay, let me just write these lines very quickly. Max, we need to do the max between the expansion factor of the heap multiplied by the heap size we currently have, and then we need to pass in the needed space, and then after that we need to align whatever this is, right? Something like that, maybe. Hmm. Okay, I guess I'll just leave it like this and then add this comment to add the alignment here. And then we're just gonna code here expansion space, expansion size. Okay, perfect. We'll just leave it like this for now. Um, let's see. Are you hallucinating? Oh, whoa. There's a lot of messages. Scratch and whack ASMR while eating a wooden back stretch. Whoa. That's a lot of words. Okay. No, when it's happening, you sure you're muted? Or you okay, I'm sure I was muted, probably. Nick Vorsa, thanks for the stream. Oh, thank you, Nick Vorsa, for hanging around, and thank you everyone for visiting the stream. 6 viewers now, like it's incredible. I usually average like 1 or 2, so having 6 people here is amazing. Glad that we're growing, and I hope everyone is sort of learning together with me, and that everyone is able to provide comments too, because I've detected that many of you come into the stream already knowing a lot about memory allocators. So I'm actually the one that's learning the most. So thank you for that and for your contributions. Um, X-Men Runner, you say bye bye. I will come back unless it's like 6 your time. Yeah, it is 6 my time. Like it's 5:45 p.m. my time, and I need to go now. Please read this one. No problem for joining. I love learning. Okay. Yeah. Thank you, everyone. Thank you, especially uh, to Nick Vorsa. Your help has been very, very appreciated. There was also Stricknid, I think, Stricknid 3, and Andrew were also very active during the session. And then, yeah, you guys, like, throw all this time with the memory allocator. Tomorrow at 6:30 p.m. PST is probably the time I'm going to start streaming. That is equivalent to, let's see, 6:15, 3:30 a.m. in Europe if you are in the Italy, Spain, Portugal area. And if you're in Eastern Europe, that's equivalent to 4:30 a.m. I usually stay until midnight, so hopefully you'll be able to catch the stream. I cannot stream earlier because I would be at work, like not at work, at my internship, right? Still a college student. Um, so yeah, I don't know. We'll see you guys. And thank you so much for hanging around. This was so much fun. I'm so sorry for what happened this morning where the stream was having failures. It seems like I managed to fix it, and hopefully it stays like this for the rest of time. And yeah, thank you everyone. Bye bye. Gotta go now, unfortunately. But yeah, thank you. Bye bye.